Good afternoon, everyone. If you're just joining us, what you will see is Samuel is promoting from attendees to panelists, those of you who are science panel members and steering committee members. He is also labeling everyone. So you'll get a thing that you've been renamed, and that's just so that everybody knows who's on the steering committee and who is on the science panel. And then if you are on the steering committee, he's just noting if you're the primary member or the alternate. So lots of juicy things just popping up over there in that participant list. And while Samuel's doing that in the background, we might want to just go ahead and begin our conversation, and I can do just a couple of introductory things. I think you have on purpose, not accidentally, stumbled into today's meeting of the Utah Lake Water Quality Study. This is a joint meeting of our steering committee and our science panel. Super excited to visit with you today about two different things. We have a meeting that's basically broken up into two big chunks. Our first big chunk carries on the conversation that many of you started with the science panel when we were in person a couple of months ago, related to the charge question and response. And Kateri is going to go through that and sort of catch you up on what the science panel's been up to overall there. Want to alert you that you will, it's going to be drinking from the fire hose right there. And at the end of that conversation, you'll have an opportunity to let us know if there are specific questions, charge questions that you as the steering committee would like to spend some more time on. We'll do that. So you don't have to feel totally panicked if you didn't read the report. Or if, as Kateri's talking, you're like, holy cats, I can't keep up. Don't sweat it. We'll come back and give you an opportunity to tell us where you'd like to talk more. So all of that is first things here. And then we're going to take a break around 2-ish, depending, give or take a couple of minutes. And then we have the second half of our meeting dedicated to a conversation about atmospheric deposition. And this will be presentations from two of our science panel members representing the majority and minority perspectives. And Samuel will tee that one off with a here's how we got there. As we always do, we will take public comment. You will know that you are a member of the public. If you have not been promoted to panelists, I'll be happy to take your brief thoughts, questions during the noted public comment opportunities on the agenda. You'll see there's a few minutes there after the charge question conversation. And then there's a few more minutes after the atmospheric deposition conversation. And then we usually do our best to leave about 10 minutes just for go backs on anything related to public comment. That is a lot of ambition in a very small amount of time. So given that we need to breeze through this, I'm going to go through for introductions, and I'm going to start with the science panel members, ask you to introduce yourselves, and then I will just call on those of you who are on the steering committee and ask you to introduce yourselves. If you could just say who you are and the entity you represent, that will make it most expedient. Before I jump into that, I do want to invite our co-chairs first to introduce themselves. John Mackey.
Hi, good morning, good afternoon. John Mackey, Division of Water Quality.
Thank you. Hi, Luke.
Hi, Luke Peterson, Utah Lake Authority.
Good to see you. Science panelist, Mike. Oh, Mike, you're chewing. Let me go to Theron first. Theron.
Yeah, I'm Theron Miller, representing the Wasatch Front Water Quality Council.
Fantastic. All right, Mike, you're
up. I'm Mike Brett. I'm a professor of civil and environmental engineering at the University of Washington, and I'm a member of the Independent Science Panel.
Great. Hans.
Hans Perl, University of North Carolina, Institute of Marine Sciences, all the way over on the Atlantic. We're probably about as cold as you guys are over there. And I'm on the science panel, and I've been on there for a long time.
Fantastic, and we've been delighted to have you. And you always wear a sassy shirt, which brings me joy. Hey there, Thad.
Hello, Thad Scott, Baylor University.
Good to see you. Hey, Mitch.
Good morning or afternoon. I'm Mitch Hogsett, a wastewater engineer with JUB Engineering, and I'm part of the Independent Science Panel.
Excellent. And Janice, I see that you're not on camera, but I just see your there you are, lovely. Hi.
Hi, Janice Brainy, Utah State University.
Excellent. Good to see ya. And I think that covers all of our science panelists. Now I will go through just in the order you appear in my list for steering committee members. Good afternoon, Dave.
Dave Norman with Lehigh City.
Good to see you. Gary.
Gary Calder, excuse me, Gary Calder with Provo City Water Resources.
Afternoon, sir. Hey, Brad.
Brad Stapley, Springville City.
Charles. What just happened there? Whoa.
Charles Davenport, Utah County.
There you are. All right. Hi, Gerard.
Gerard Yanks with Central Utah Water Conservancy District.
Good to see you. David. Barlow, where you went? There you are.
David Barlow, Timpanogos Special Service District.
Good to see you. Hi, Heidi.
Hi, Heidi Hoven, National Audubon Society, Gilmore Sanctuary, representing conservation and environment.
And indicating commitment by joining us from a clearly a vehicle that I hope is not
yes,
moving.
I'm just about to hop inside now.
Okay. Excellent. Hi, Jay.
Jay Olson, Utah Department of Agriculture and Food, representing agriculture.
Good to see ya. Jesse.
I'm Jesse Stewart, representing the Utah Lake water users. I think I'm like irrigation and ag. I can't remember what my official group is. So,
Well, now you've failed the pop quiz, but we'll let you stay in the meeting anyway on account of we like you. Mike. Rao. There you are.
Rao, Central Utah Water Conservancy District.
Good to see you. Reed.
Yeah, Reed Price with the City of Orem.
Lovely. Rich.
Rich Mickelson, Timpanogos Special Service District.
Good to see you. Hi, Sarah.
Hi, Sarah Siegert with the Utah Division of Wildlife Resources.
And Ben, did we miss you in my alphabetical journey?
Ben Steierman with the Division of Forestry, Fire, and State Lands.
Lovely. Did anyone else hop on that I missed? All right. In that case, I'm Heather Bergman, and I am the facilitator of the Utah Lake Water Quality Study. And Samuel, if you'd introduce yourself and then maybe transition things over to Kateri, if you would.
Great. My name is Samuel Wallace, and I am part of the facilitation team for the Utah Lake Water Quality Study as well. I think before we transition it to Kateri, we have a couple slides to just tee up a little bit of just kind of a process update and reminder for everyone. But Heather, I think you have a couple slides before I jump into it. So
that sounds like something I would have. All right. So steering committee, we don't get together quite as much of late. So a couple reminders here, super excited to readdress the process commitments that you all have made to each other way, way back in the day. This includes seeking to learn and understand each other's perspectives as opposed to listening to debate and disagree, try to understand even if you don't agree. We, of course, encourage and in fact require respectful, candid, and constructive discussions, looking forward to hard questions and big ideas delivered in a civil and constructive way. If we find ourselves at a disagreement and need to figure out a path forward, let's try to resolve those differences and reach consensus. We do have the option to do voting, but that's no fun. It's much better when we can find a way to get to common ground. As a general rule, we strongly encourage members of both the science panel and the steering committee to talk together and explore things in a group rather than doing things in isolation, and make every effort to avoid surprises, whether that is in the meeting with here's some news or in between meetings in a collaborative environment. Folks generally benefit from a little bit of a heads up from our collaborative partners. So ground rules, some of these are somewhat duplicative with our operating principles, but just to be make sure we're all thinking the same is today we are talking about two things. charge questions, and atmospheric deposition. Lots of other fun things to talk about later, but right now we're going to focus on those two things. We're going to have one person speaking at a time, and given that there are 30 plus people in this meeting, you'll find that you will not be able to unmute yourselves. We're going to make sure that we're sort of doing some gatekeeping there, so you'll just need to raise your little e-hand when you're ready to jump in. If your camera's on and you just want to go like this, that would also signal to me that you wanted to jump on in. We like to have a balance of speaking time for all of our folks who want to jump in. So please be as brief as you can, both if you're asking a question and if you're just providing comment or answering a question. Listen with respect. Listening with respect. Let me just tell you what that looks like. That looks like a nice even face and not like grr and like that. That's not respectful listening. So just like, be chill. And be civil again in our facial expressions, in the things we say to and about one another. It is perfectly acceptable in a collaborative environment to disagree and to disagree strongly, but there's no reason to be ugly. There's no reason to besmirch one another's reputations, intelligence, or footwear, whatever. We're just going to be real pleasant here while we jump into this conversation. Keeping side conversations to a minimum is a ground rule that is most appropriate for an in-person meeting. And a virtual meeting, we talk about keeping things out of the chat. And for the purpose of today's conversation, we've actually turned off the chat so we can all focus on the cool stuff that's going to be happening with our presenters. And the virtual version of keeping your cell phone off is maybe close that email inbox that I know you secretly have turned on in your other window. Just close that down so you can give us your full attention today. Samuel?
Great. And with that, I'm going to give just a really brief reminder of where we are in the process, what's come to date, before I turn it over to Kateri to give an overview of the charge question responses. So just as a really high level, there are 3 phases to the Utah Lake Water Quality Study. The first one is phase 1, which is data gathering and characterization, which is a phase that is complete. And phase 2 is the development of numeric nutrient criteria. And that's the phase that we've been in as as the science panel has been conducting scientific research and conducting analyses to help develop and inform the numeric nutrient criteria. So this is the phase that we've been in over the past couple years. And then a reminder that we do have a third phase for implementation planning, which is a task of the steering committee to think a little bit more about how will we actually what type of management actions will we need to implement in order to achieve the numeric nutrient criteria. And this is actually a phase that we are hoping to launch in 2025 in the coming months. So just kind of a reminder of this really high level of the 3 phases of the Utah Lake Water Quality Study. Just a really quick zoom in on phase 2, and really phase 2 has has 2 main responsibilities. And this is what the steering committee charged the science panel with, I think back in 2020. And those 2 main responsibilities were to respond to charge questions posed by the steering committee and then develop and implement a framework to recommend numeric nutrient criteria for Utah Lake that will protect its designated uses. And so for today's meeting, we're focusing a lot less on the second bullet and a lot more on this first bullet, which is one of the primary responsibilities of the science panel. So just a quick reminder of the charge questions and the timeline for what got us here. Back in June 2019 is when the steering committee first developed the charge questions and tasked the science panel with developing responses. In August of 2020, the science panel, over several meetings, developed the strategic research plan. And the goal of the strategic research plan is to fill data gaps and address scientific uncertainty in responding to the charge questions, as well as developing the numeric nutrient criteria recommendations. From 2020 to 2024, the science panel oversaw the development of the strategic research plan studies, which I'll give a quick reminder of in a second of what that entailed. But this involved working with primary investigators and research to conduct a series of studies over the 4 years. In the interim, as the science panel was working on those SRP studies, they also developed interim charge question reports in 2021 from August to October. So this was using the existing evidence at the time to, just tackle a first attempt at the charge question responses. And if you all recall, in January 2022, we had a joint steering committee and science panel meeting to review and discuss those interim charge question responses. So between 2022 and right now, 2025, the science panel worked on conducting a series of studies. The ones on the left are those that were involved with the strategic research plan. This included the sediment nutrient interaction study, carbon, nitrogen, and phosphorus budget study, the bioassay study, a study on littoral sediments, on phosphorus binding and paleolimnology, and then 2 additional studies that were conducted by partners outside of the science panel, but were relevant to discussions on charge questions, are the Timpanogos Special Service District Limno Corral study and the atmospheric deposition study conducted by the Wasatch Front Water Quality Council. This is just the list of SRP studies that the science panel oversaw, but these charge question responses also include additional empirical analyses, Utah Lake literature and technical reports, and literature from similar lakes. So these charge question responses synthesize a lot of different sources, both those from the strategic research plan as well as those that weren't that came from other sources as well. So that leads us to this latest round of the charge question responses from April to May 2024. Science panel members met in subgroups to update the charge question responses using new available data from completed studies, and have worked diligently on that. And now it is January 2025, and we are having this joint meeting to review and discuss the updates to those charge question responses. The other main task, which I'll kind of breeze through since it's not a focus of today's meeting, but is important, is the numeric nutrient criteria recommendation itself. This is being implemented through a framework called the Technical Support Document. This document provides the technical basis for the development of numeric nutrient criteria to protect the designated uses. That's recreation, aquatic life, agricultural, and downstream uses. This document includes several analyses that will support multiple lines of evidence in developing that numeric nutrient criteria recommendation. I won't go through this too in depth, but there's 3 different lines of evidence the science panel is exploring. This includes reference-based materials that take a look at things from paleolimnological studies, as well as utilizing the Utah Lake nutrient model once it's ready. What's called stressor response analyses, which is using some statistical models to assess the relationship between several different variables, and then additional scientific literature. I won't go too into depth because it's not the focus today, but we will, I'm sure, be diving into this in future steering committee meetings. But the current focus of the science panel is taking a deeper look at these stressor response analyses. We've had a couple subgroup meetings in the past month to continue work on this effort. So just upcoming next steps. The science panel, we are sharing the charge question responses with the goal of finalizing those in the near future. And the science panel also continues to work to implement the numeric nutrient criteria framework to generate those recommendations. And as I alluded to earlier, the steering committee is going to begin the implementation planning phase in 2025, hopefully in the near future. So that brings us to what we're doing today. Really, the objectives of the meeting today are to review the science panel updated charge question responses and to gain some insight and better understand the science panel discussion on atmospheric deposition research and estimates, as well as hearing from different scientific perspectives on this topic, all with the goal of laying the scientific groundwork, which will help inform your conversations as the steering committee in the future when it comes to things like implementation planning. So with that, I don't think we're actually going to jump into questions right now, given the time. So I am going to now hand it over to Kateri to give us a presentation on the updated charge question responses. So Kateri, the floor is yours.
And you can introduce yourself, since we were going to do it earlier, and then now it's all you, girl.
Sounds great. Hello, everyone. I'm Kateri Salk. I am a limnologist by training, and here today representing Tetra Tech, who's providing the technical support to the science panel for all sorts of activities, including the charge questions. So that's what you'll be hearing from me about today. This will be a synthesis of all of the different responses to the charge questions that the science panel has put together. As Heather mentioned, it's very broad, and a lot of different questions are covered in the presentation, and there will be opportunities to dive in if anybody's interested in learning anything more about a specific topic. As you might recall, there were 4 overarching charge questions that the steering committee posed to the science panel. Question 1 related to the historical condition of Utah Lake, in particular, what it looked like before European settlement. The second related to the current state of the lake, with a lot of different subtopics in there, which we'll get into. Question 4 related to potential future conditions of Utah Lake with management constraints. And then question 3 related to what additional information is needed, and it was sort of a data gaps exercise. This was addressed as a part of the strategic research plan, and several studies, like Samuel just outlined, came out of that effort. So we'll really be focusing on questions 1, 2, and 4 with the report if you had a chance to review it. Along with every charge question, the science panel developed a series of responses. These were divided into 2 sections. So the first section involved evaluating evidence. The focus here was the technical basis for all of the different studies that might inform that specific sub-question. These could be from Utah Lake, these could be in related ecosystems. It sort of depended on the question. This section also includes figures and tables from the different cited studies that serve as support for that evidence evaluation. The second section of the charge question response involves a synthesis, which is a 1-paragraph summary. It's a more plain language and non-technical response that provides sort of an overarching response to the question. This also included an assessment of the science panel's confidence in the response. And I'll go over what the confidence evaluation looked like. So the confidence evaluation involved referencing an uncertainty guidance document that the science panel put together as part of phase 1. There are 3 different big elements of confidence evaluation that are pictured as these 3 different axes on this matrix today. The first axis on the X, or the horizontal, is the amount of evidence. So how many studies, how robust are those studies? What amount of evidence is available to answer that question? Along the upper axis, the vertical axis, we have the agreement among evidence. So if there are multiple sources of evidence, how well do they agree? And this could be sources of evidence that have the same approach or different approaches, and what conclusions are they coming to? The more evidence and the higher the agreement among evidence, the higher the confidence in the response. And then finally, the third axis here, which is going back in the Z space, is how much consensus was achieved among science panel members. So let's say there was a lot of evidence that all agreed. There could still be some interpretations that might make a response to a given question different among whoever is interpreting that evidence. So that's where the consensus bit came in. So the higher the consensus among science panel members, the higher the confidence is possible with that response. So those are all the things that came together in evaluating confidence. As you might tell, it's fairly qualitative, so oftentimes it involved a little bit of debate among science panel members. But almost every response that you'll see in this slide deck will involve an estimate of confidence. Just to note, in general, the science panel came to a conclusion of high confidence in many cases. This often involved when we had direct evidence to evaluate that was from Utah Lake, using well-established or well-respected methods in the literature. In some cases, there was higher confidence associated if Utah Lake behaved similar to other lakes and how we would expect based on sort of the general theory of the literature. And then if there were multiple studies or multiple different lines of evidence that were provided, if those findings were consistent among studies. So those were the sort of factors that typically resulted in high confidence. As well as if there was a conclusion that was made that was sort of based on a big picture statement rather than something more detailed, that often was able to result in higher confidence. When you see lower confidence, it's often because there were really, really specific items to be answered within the question, or there were some complex and interacting drivers. So those were the things that sometimes resulted in lower confidence. There are some elements in here that you'll see as part of the report, as well as this presentation, that have not been assessed for confidence yet, and that's because there are ongoing or upcoming studies that will inform the answer to that question. So I'll know where that's the case. All right, let's jump in. I mentioned that there were sub-questions for each individual question, so I've got those laid out right here, specifically for question 1 this time, and we'll use these as sort of touch points throughout the presentation. So regarding historical condition, there were several sub-questions. The first question relates to what we know about the historical diatom and macrophyte communities from the pre-settlement period in Utah Lake and how those relate to the nutrient regime of the lake. The next one relates to historical nutrient and other elemental concentrations. Again, figuring out what things look like historically compared to now. The third sub-question relates to the population and growth trajectory of carp over time and what impacts they have on the nutrient regime of the lake. And then finally, what do investigations of phytopigments, which are algal pigments, and DNA in the paleo record tell us about historical conditions in Utah Lake? So for each of these sub-questions, I'll have 1 or 2 slides and we'll cover each of these. Again, it'll be a lot of information, but hopefully enough detail to get an idea at those responses to the questions. So first, just a summary of the chronology of the lake. And in a lot of cases, for the historical condition, you'll see these graphs where we're depicting present day at the very top of the graph, and then going back in time as you go lower down into the graph. And then, whatever the other axis would be, population in this case. So a couple of summary points. Utah Lake has experienced some major phase shifts over time. The first major phase shift occurred when Europeans settled the area and carp were introduced. This happened in the late 1800s, early 1900s, and those are depicted as the wagon and the fish, respectively, in this graph. There's also been a shift to more cyanobacteria dominance in the algal population around the middle of the 1900s. There's obviously been a huge increase in population, which is shown along this x-axis of this graph in the watershed, which has caused a lot of different changes in the watershed as well as human pressure. Finally, there have been changes in wastewater loads. As more people have come in, there's obviously more wastewater. And then alongside that, there's also been improvement of treatment technologies. So a reduction in nutrients for a given amount of wastewater. Second major point is that trophic status has increased to more eutrophic conditions from pre-European settlement to present. Multiple indicators have supported this. And then finally, climate change has impacted both temperatures and precipitation in the basin, so that has resulted in impacts to Utah Lake as well. So getting into details, here's some information about diatoms and macrophytes. So for diatoms specifically, there were 3 independent studies that were done on sediment cores that showed that, number 1, there's been a historical dominance of benthic and epiphytic species, which means species of diatoms that live on the sediment and on top of submerged macrophytes. This has shifted over time into a dominance of planktonic species or species that float in the water. And that really indicates a shift from these clear conditions where light is penetrating down to the sediment to these more murky conditions where we're not getting as much light penetration. There's also been a change from more sensitive taxa to more nutrient tolerant taxa over time, and that's consistent with an increase in the nutrient regime, more eutrophication. As far as macrophytes go, there's a large body of evidence, including physical remains, historical accounts, and elemental concentrations and isotopes, which the latter of which you see on the right-hand side here. These support the historical presence of both submerged and emergent macrophytes. The science panel assessed this with high confidence in general, but there's a little less specificity that we know about exactly where macrophytes occurred along the lake, especially for specific areas in the main basin. Moving on to elemental concentration and isotopes. There were, again, 2 major phase transitions in the lake in terms of biogeochemistry. We have this shift associated with European settlement and carp introduction, and then we have this timing of eutrophic conditions and cyanobacteria dominance. That's displayed across several different elements and isotopes. We've seen that phosphorus, nitrogen, and carbon have increased over time in Utah Lake sediments. And interestingly, some investigations of carbon and nitrogen isotopes have supported a shift from this macrophyte-dominated state to a phytoplankton-dominated state. And then also there's been increasing prevalence of wastewater in the lake nitrogen supply as evidenced by increasing delta values of nitrogen over time. There's been some investigation into specific metals, which just in general, I'll sort of go over the details for now, but there have been some major changes in redox in the lake, meaning oxygen conditions in the sediments, which has been variable by location. There's some hypotheses as to why that is and how that's happened, which we'll get into in future slides. Given the multiple lines of evidence that have come to similar conclusions, the science panel assessed this question as having high confidence. Next, we'll get into the paleolimnological record for carp. So again, carp were introduced in the late 1800s, which aligns with that first lake transition. In terms of looking at metal concentrations, particularly iron and manganese, these have provided evidence that sediments were more stable and had more of these oxygen reducing conditions pre-carp, because carp had the ability to stir up the sediments via bioturbation. Environmental DNA analysis was attempted, but was inconclusive. So this was an attempt at getting some more information with DNA, but wasn't successful in this case. The science panel assessed the paleo record for carp as having medium confidence in those conclusions, simply because it's a little bit difficult to parse the specific impacts of carp separately from other human drivers, because a lot of things were changing in the basin around the same time. So a lot of it we can hypothesize is due to carp, but maybe not the specific magnitude and mechanisms. What have we learned from the paleolimnological studies about historical water quality and trophic state from photosynthetic pigments? So you'll see here, this is just an example from Provo Bay, but there have been analyses in other locations as well. Again, going from present day at the top to into the past as we go further down. So what you'll notice across all of these different pigments along the x-axis here, the photosynthetic pigments have increased from baseline to present. You'll see I've labeled a few specifically that are associated with cyanobacteria, those taxa that produce harmful algal blooms, nitrogen fixing species, which are often associated with the cyanobacteria as well, an increase in diatom phytopigments, and also an increase in these green algae associated phytopigments. Again, this is supporting that idea that we have these two phase transitions, one around the turn of the century and one in the mid-1900s. Another interesting point, again, perhaps attributed to carp, is that degradation of these pigments has increased due to the sediments not being as stable as they used to be. The science panel assessed this response with high confidence. Okay, I've sprinkled a few of these throughout the presentation. If anybody has any questions thus far, and maybe I'll turn it back over to Heather or Samuel if they want to field any questions.
Heather, you're on mute. Oh, I can't. I see what's happening.
There it is. Thanks so much. So we have a couple of minutes for quick questions, and then we'll move on. And if we can't get to your question right now, Samuel did enable the chat, so you could drop your question in the chat. Rich, question, go. And then Samuel, do you have to unmute? Okay, there we go.
I just had a quick question on that historical water quality. You know, it looks, that one slide back, it looks like it goes all the way up, and then in 2020 it jumps down. I'm just curious, do you have any explanation on those?
Yeah, so I think we'd have to go back into the specific studies, but there's often a little bit of differences that happen at the very top of the sediments, just because they're the actively interacting with the water column layer of sediment. So I'm not exactly sure, and I think we'd have to look at exactly when that was dated. But you'll see that in those areas where we see that slight decrease, that's over a period of maybe 20 years. So I'd hesitate to make any sort of grand interpretations based off of that, but we can certainly look back into this publication specifically to see if there's any conclusions they made there.
Thanks, Kateri. Gary, go ahead. And hold on, I have to ask you. There you go. You should be able to unmute now.
Okay. Back on page 7, Can you hear me okay?
Yep.
Sorry. Back on page 7, you said there's an increase in cyanobacteria since 1950. What's your basis of making that type of comment? Because before 1950, how would we know?
Yep, so a lot of that was based on the ability to look at some of these specific pigments, which you see here. There's also evidence from the isotopes in nitrogen fixation that we can infer, and then there's also the DNA evidence as well.
Okay, I was just okay.
Yeah. So several lines of evidence.
I saw
and I
that
don't think
way
that
up front,
appeared in-
and so okay.
Yeah, I don't think either one of these figures showed that specifically, but I know it's in the report, and I'd be happy to grab that for you, and we can come back to it.
Thank you.
Thanks, Gary. All right, we'll take two more questions, and then we'll move on. We'll do brief questions, brief answers. Jesse, go ahead.
Yeah, thanks. Yeah, I just have a question with some of the changes you've talked about. So I think there's evidence that the lake got really, really low in the 1930s during the drought. I know a lot of the cotton canyons and things dried up. How does that play into, or did you take that into account when you're giving your core samples and as far as deposition?
Your audio is a little garbled there. Kateri, did you get the question?
I think it did, yeah. So the fact that the lake level was very low in the 1930s, and if that had any impacts on the sediment cores. I guess one thing to note is that a lot of times, we're looking at a very large range of years along a very short amount of space in the core. So it maybe a single few years might not show up quite as well. I might actually, I know Janice is in the room. I don't know if Janice wanted to maybe field that question since she was leading a lot of the sediment core analysis.
Janice, you want to take a run at that? I'm pressing the ask you to unmute button. You should be able to unmute now.
Yeah, we did take that into consideration. So we took cores from 5 different locations. We are certain that some of the main sites that where we made our interpretations from, that they were not dried out during that 1920s period. Based on the historical maps and the depths of the cores that we took.
Super. Thanks, Janice. And then Jay, our last question. If you have any questions after Jay, drop those bad boys in the chat. Jay, if you'd unmute, please.
Can you hear me?
Sure can.
Okay. As I was going through, and I did not get through all the stuff that was sent out, I was trying to understand, there's basically 2 questions. On the core samples, is there kind of a chart that says this sample is so many centimeters and that represents this time period? Because I was confused on some of that, on what time period they represented. And the other was on the carp. It appears to me from everything I read that the carp are the main concern. And if we had the carp gone, we could work on the rest of it and maybe come up with a better solution. Am I wrong, or did I misinterpret the data?
Yep. So yeah, Jay, on your first point, isotopes were used to date the cores. So based on how much transformation those isotopes happened over time, those radioisotopes, you can assign a specific date to the cores. So I'm trying to remember if I have those in my, I think I have mostly ones with dates in this presentation, but yeah, sometimes you'll see where we have specific depths noted in the cores, and those were all dated so that we can assign at a given depth, here was the year. And so then you get this translation back to years, which you see on the bottom graph there. So it's done through isotope dating to figure out the what time period is represented by which depth of the core, and that varies over space as well. So that's why it was important to do the dating on each core individually. On the point of carp, it's certainly no, based on all of the information that was evaluated by the science panel, it's clear that carp have had a big impact on the lake. There have been a lot of other changes in the basin and in the lake concurrently, so it gets pretty difficult to parse exactly what the problem of carp was alongside other things and what the impact would be if carp were completely removed in the absence of other factors as well. So definitely a complicated question, but it's very clear that carp have been a big cause of change in the lake over time.
Thanks, Kateri. All right. Anyone else? If you have questions on that stuff, drop those bad boys in the chat. In the meantime, we'll let Kateri move on. What you got next?
So next we get into current condition. And like I mentioned, this was the biggest topic that has quite a range of subtopics within it. So I'll go through each subtopic specifically from here on out. So question 2.1, this is what are the impacts of carp on the ecology and nutrient cycling in the lake, and how has that changed with removal efforts? So Jay, thank you for your question. This was a very good springboard into this topic. So the first sub question within there, which I won't read all these off specifically, but each slide will cover one of these sub questions. So the contributions of carp to nutrient cycling. So first of all, just as a primer for everyone, carp have decreased from a high of around 50 million kilograms in the early 2010s down to under 20 million kilograms in 2018 and 2019. There have been increases in carp since then, but as you might notice from this graph, the trends in carp tend to follow a little bit with lake level decreases and increases. So we're back up in carp since that low, but certainly not up to those highs. And this is a lot due to that, due to the carp removal efforts that have been going on in the lake. So how might carp impact nutrient cycling in Utah Lake? So as part of some of the data analysis that was done for the Utah Lake Water Quality Study, there were some lake-wide estimates that were estimated for how much nutrients carp excrete through their waste each year. So you'll see those ranges here. It's quite a lot of kilograms of nitrogen and phosphorus that are moving through moving through carp on a yearly basis. So it's certainly carp are having an impact on nutrient cycling and changing of the forms of nitrogen and phosphorus. I will note that this represents a recycled pool of nutrients, meaning that it doesn't represent a new source when there is excretion that occurs. So it is a recycled source that's cycling through the lake. The science panel assesses with medium confidence, just due to a lot of the assumptions that had to be made, which result in those fairly wide ranges of estimates in excretion rates. So what has been the impact of carp removal? Given that we know that carp have had a huge impact on the lake, they have a negative impact on macrophytes. They not only disturb the sediments through bioturbation, but they also might actually feed directly on macrophytes. So removal of carp represents a relief of that negative pressure on macrophytes. Carp removal efforts have also had a positive impact on the lake in other ways. So in response to carp removal, macroinvertebrate, both abundance and diversity, have increased, and large-bodied zooplankton, which are a preferred food source for fish such as the June sucker, those have also increased. Removal efforts have also had a positive impact on water clarity and have increased green algae abundance. Just to note that there has not been a positive or negative impact on harmful algal blooms in response to carp removal. The science panel have assessed this with high confidence, partly due to the great work that the June sucker recovery program has been doing. The next sub-question under current conditions is thinking about what are the environmental requirements for submerged macrophytes currently present in Utah Lake, and what are the impacts of reduced water clarity specifically. So in terms of environmental requirements, currently Utah Lake has a relative low presence of macrophytes. There are some established beds in shallow areas, but nowhere certainly close to where they were historically. So that current absence has been attributed to several factors. The first is phytoplankton primary production, shading out the capacity for light to reach the bottom and to allow for submerged macrophytes to photosynthesize. Carp bioturbation, not only stirring up sediment, but also disturbing the sediments for root establishment. And then sediment resuspension due to wind and wave action. So we know that increased water clarity is needed to reestablish macrophytes through several different lines of evidence, including evidence from the literature, monitoring data directly from Utah Lake, and scenario modeling, one of which you see on the right-hand side here. The science panel assessed this with high confidence. Thinking about what might the lake elevation, or how might lake elevation play a role in macrophyte recovery? So we know that Utah Lake shifts quite considerably in the lake level. You'll see that here on the left with the annual elevation on the x-axis, and then the time by year on the y-axis. So we see a lot of fluctuation. We know that some emergent macrophyte species are more resilient to lake level changes than submerged macrophytes. But if you are in an area that is shallow enough where you're getting enough light to the bottom, that also might be an area that is periodically dried, which presents a barrier to submerged macrophytes. Also to note, lower lake elevations are also associated with larger harmful algal blooms in Utah Lake, which could also play an impact on macrophyte recovery. The science panel assessed this with high confidence. And now we'll get into the interactions between carp, wind, and macrophytes. So in just thinking about water clarity, how much turbidity is due to different factors. So in our report from 2021, we noted that the majority of the reduction in water clarity or turbidity in Utah Lake is made up of non-algal turbidity, i.e. Sediment resuspension. There is a substantial proportion of that turbidity that is made up by phytoplankton or algae, but the majority of it is due to sediment resuspension. So we know that both wind and carp have a negative impact on macrophytes and particularly on sediment resuspension, which reduces the light environment. Wind is the primary hypothesized driver of this lack of water clarity. We do see a positive relationship between wind and turbidity in the lake, but we also know that bioturbation does kick up sediment as well. There was a carp exclosure experiment that was done, which wanted to evaluate the impact of carp specifically, but it was noted in that study that those exclosures also reduced the impacts of wind and waves. So again, really difficult to sort of parse those two things separately. Final thing to note here is that macrophytes could have a positive feedback on sediment stabilization and water clarity by stabilizing the sediments with their roots, as well as attenuating some of that wave energy. So the more sediment stabilization happens, the better water clarity could be, which could also result in more colonization. So a positive feedback loop there that could be possible. Across all of these different analyses, the science panel assessed this response with medium to high confidence. I'll pause there for any questions about carp and macrophytes.
All right. Sarah has a burn-in question. Go ahead, Sarah. Oh, did I do it twice? How about now? Can you unmute? There we go.
Okay. Yeah, I have a couple of questions, but I'll start with the impact of carp on nutrient cycling. How much of that is unique to carp and how they cycle nutrients versus any fish in the system? It's just that they happen to dominate the biomass. Does that make sense?
Yeah, good question, Sarah. That slide. Yeah, so the question was about how much of this, these estimates for carp excretion that were done are specific to carp versus other fish. So the calculations that went into these numbers were specific to carp. So for the specific species in Utah Lake, so we gathered those that are specific to carp, but it is a really good point that other fish do excrete nutrients as well. Those were not included in these specific estimates, but there's obviously nutrients moving through all places in the food web, and so there would be excretion coming from other fish species as well. But yeah, as much as was possible, all of these calculations were done specifically for carp because and using their conversion factors for carp.
Yeah, I would just want to make sure that if we're making generalizations about what, if we removed carp, then they would not be excreting those nutrients. But if they were replaced by another species, they might still be, some sort of fish might still be
Sure, yep.
processing those nutrients.
That's right.
I had one other quick question or comment. Can I
Go ahead.
here? Just thinking about the relative effects of wind and waves versus carp bioperturbation on resuspension of sediments. I'm wondering if any thought had been put towards looking at the new Provo River Delta, which is somewhat more protected, but currently is open to carp, and possibly looking there, though the sediment, I mean, it's a different kind of ecosystem, but just thinking about how the Delta might fit in with all of this and act as a little microcosm or mesocosm.
Mm-hmm. Yeah, the Provo River Delta is a great example of sort of a living experiment of how all of these things are playing out, where you have this protected area that could be, it is spawning and rearing ground, and also has had some success in macrophyte recovery. But obviously there is the capacity for carp to come in. We haven't had any, at least formal studies or data that have come in that the science panel has been able to incorporate into the charge questions response, but it's certainly a place that could serve as a really nice case study into how some of these recovery efforts and parsing some of these drivers might work well. I don't know if any DWQ folks would want to weigh in on that question specifically.
Hold on, I gotta get there. Scott, go ahead.
Hi, everyone. Scott Daly with Division Water Quality. We haven't talked specifically about evaluating the Provo River Delta, but we are looking at differences that we see in characteristics in Provo Bay versus the open water. Provo Bay is somewhat more sheltered from the wind, a little less wind turbation, for example. So pretty interesting case study.
Thanks, Scott. All right, Theron, question or comment? Go ahead.
There we go. Yeah, just to comment on that, on the carp excrement question. So, the latest number I believe I've heard is around 85% of the biomass in the lake is carp. And so if you remove that, though, it's likely, because there's still a pretty diverse population of other, even though they're not endemic species, but that biomass would largely be replaced by other species just to make up for that carrying capacity of the lake. So totally may not make up a lot of difference in the overall excretion rate between carp and other fish. At least over time, it would probably adjust to a similar rate, is what I think the general consensus is among fish guys.
Thanks. Thanks, Theron, AKA Fish Guy. Anyone else have questions or comments before we move on? All right.
Okay, great. We'll keep moving with current condition. The third sub-question under that bullet is thinking about the linkages between changes in nutrient regime and harmful algal blooms. I won't belabor each of these sub-questions here, but you'll see a slide on each of them. First question related to where are harmful algal blooms occurring in Utah Lake. The great thing is that we have some awesome direct monitoring data through phytoplankton cell counts, which you see on the upper panel here. And then there's also data from remote sensing. Utah Lake is large enough where we have great remote sensing data that we can use to assess cyanobacteria and harmful algal blooms. So as you might be able to see from these two graphs, which again represent a snapshot, but can also be used to infer general conditions. Harmful algal blooms are most common in Provo Bay, in Goshen Bay, and then in the eastern portion along the main basin. These are also areas that are associated with watershed loading sources, and then they also consistently have more nutrient enrichment than other areas of the lake. The science panel assessed this response with high confidence. The next question relates to which nutrients are controlling harmful algal blooms and when. So just to start off, Utah Lake does display this sort of typical lake pattern in eutrophic systems that have a specific phytoplankton taxa that are dominant during certain times. So we generally see a dominance of diatoms in the early part of the season in the spring, followed by a midsummer bloom of cyanobacteria, which have the capacity to produce toxins, and then followed by a late summer bloom of green algae. So that's, again, pretty typical in the literature, and Utah Lake behaves similarly there. There have been several studies that have addressed nutrients, specifically Zach Onderud's project that evaluated specific nutrient bioassays that showed that phytoplankton growth is sometimes limited by nitrogen, sometimes limited by phosphorus, and sometimes both. And this limitation tended to be variable across time and space. So that really shows that both nitrogen and phosphorus are important in controlling phytoplankton growth and harmful algal blooms in Utah Lake, but it really depends what time of year and what location as to which element or both are controlling it at a given time. The science panel has high confidence in this due to the multiple different types of evidence that were available to answer the question. There's also a question in here that dealt with other factors that control harmful algal blooms apart from nutrients. And I'd encourage everyone to go read the report if you want a lot more detail on this. But the general points here are that climate change is expected to worsen harmful algal blooms due to higher temperatures, which favor cyanobacteria, and then more variable precipitation. So we have these alternating periods of drought and then high precipitation, which can bring in nutrient sources from the watershed. Grazing pressure from zooplankton was an interesting topic to address. In certain times of year, the zooplankton have the capacity to limit phytoplankton from a top-down perspective. But in the summer in Utah Lake, the phytoplankton growth is high enough that the grazing pressure from zooplankton is not enough to keep it at a low level. This was assessed with medium confidence just because of a lot of the different sources of variability and the interacting drivers. The next question with regard to current condition is how are sediments affecting nutrient cycling in Utah Lake? And I believe this was the topic that the science panel spent the most time on. So it was a really rich area of discussion in developing these charge question responses. Again, I'll have a slide for each of these sub-questions. So first, what is the role of calcite scavenging in the phosphorus cycle? Utah Lake is really interesting because calcite scavenging is a process that's active here. So this is where phosphorus is binding to calcite minerals. It's noted that, and you'll see this in the top figure here, that 2/3 of sediment phosphorus is in calcite minerals. It's the purple fraction that's noted in this graph. Any sediment that's bound to calcite minerals are non-bioavailable in that form. Theoretically, this process is an equilibrium reaction, meaning that phosphorus can sorb and desorb from those calcite minerals. However, at the high pHs that are observed in Utah Lake, this tends to be a one-way process. So it's basically a permanent one-directional process in the conditions that are present in Utah Lake. This means that the phosphorus is subject to burial once it's bound to calcite in Utah Lake. Additional analyses that were done by Josh Lamont as part of this calcite scavenging study demonstrated that sediments are capable of retaining even more phosphorus than they currently hold, and that these conditions were spatially variable. So Provo Bay has higher phosphorus concentrations in the sediments, and those sediments also have higher storage capacity. This was a high confidence response by the science panel. The next question related to equilibrium phosphorus concentrations, which represents the phosphorus concentration at which sediments switch between taking up phosphorus and releasing phosphorus. So the concentration of that was anywhere between 0.3 and 1 milligram per liter phosphorus. This was highest in Provo Bay. So again, Provo Bay had the highest concentration for that, like it does for other elements of phosphorus. The thing to note here is that at these equilibrium phosphorus concentrations, this concentration was lower than influent phosphorus concentrations coming in from the watershed, but is higher than the water column phosphorus concentrations. This means that the sediments are overall a sink for phosphorus. They take up more phosphorus than they release. This is evidenced by more than 90% of the phosphorus staying in the lake that comes into the lake. However, the sediments do display dissolved phosphorus release, in particular during the summer when those water column concentrations are low. So what do these equilibrium phosphorus concentrations mean for the effect of reducing external loading of phosphorus to Utah Lake, and what that lag time might be in reducing phosphorus concentrations in the lake? So based on these discussions, reducing the influent phosphorus concentrations below the equilibrium phosphorus concentration means that the sediments will release phosphorus until a new sort of equilibrium is reached. So the predicted impact here is that in response to decreased watershed loading, the water column phosphorus concentration will go down, but there may be a lag time to reach this new equilibrium with the sediments. The science panelists discussed long and hard about what that lag time might look like, and there's several different factors that play into that. The lag time might be shorter, say months to a few years, if that internal phosphorus release rates are maintained, and then if the hydraulic flushing rates are maintained, basically how much water is coming in and how much water is going out. The lag time might be longer if that phosphorus retention decreases in the sediments with that decreasing external load. So that could lead to longer lag time of years to decades. There are several analyses that are incoming that might help us to constrain some of those estimates about lag time, but that's the general discussion and what's captured in the report. So how do sediments behave with regard to oxygen and nutrient fluxes? So in Utah Lake, like with many other lakes, the sediments do consume oxygen, meaning they have a positive sediment oxygen demand. This tends to be related to organic matter in the sediments. So on the right-hand side, you see sediment oxygen demand, which increases with percent volatile solids or organic matter in the sediments. So more respiration, more organic material to respire. This tends to be highest in Provo Bay. Again, like I mentioned, the sediments are overall a sink for nutrients. So this is representing the net flux of nutrients. So there's more nutrients going into the sediments that are coming out. However, again, sediments do release dissolved forms of nutrients as what we're calling this gross flux. So we are seeing dissolved forms like soluble reactive phosphorus, ammonia, and nitrate coming out of the sediments periodically. The rates of these releases are dependent on several things, including temperature, organic matter. There was a very interesting study that Erin Rivers and her group did, which is one of the figures is on the right, that demonstrated that areas that are periodically dried and re-wetted along the margins have higher rates of the nutrient release. It also depends on sediment resuspension and how much the sediments are interacting with the water column, carp bioturbation. And then algae also have the capacity to drive internal nutrient loading as well. Another thing to just note is that there is a seasonal release of nitrate in the summertime, which indicates that the surface of those sediments is oxic during that time. So we're only getting generation of nitrate when we have oxygen-rich environments. So the surface of the sediments is an oxic environment, at least during certain times of year. All of this analysis was assigned as medium to high confidence, depending on which specific topic. Another question related to the impact of lake stratification on nutrient fluxes, and I'll step back for a little lake ecology or limnology knowledge here. So a classic typical lake that we see in the literature is one that stratifies during the summer thermally, meaning that the surface of the lake is warmer than the bottom of the lake, which you see this diagram here. This means that the bottom of the lake is isolated from the atmosphere, and respiration can decrease the oxygen concentrations and have all sorts of impacts on nutrients. However, Utah Lake is very shallow, very large, and gets mixed quite a lot due to wind action. So thermal stratification, like we might expect in this classic lake there on the right, this does not occur on a widespread sort of seasonal scale. So what we might anticipate as a prominent pathway in other lakes, being iron reduction as a source of phosphorus loading from the sediments, is not likely a major pathway in Utah Lake. There is potential for transient stratification, so stratification that might occur on calm days or periods of calm. This does have the capacity to alter those oxygen gradients at the sediment water interface, but not to the extent that we might see in other systems. This was a high confidence statement. The final sub-question to round out the current condition is asking about for warm water, aquatic life, waterfowl, shorebirds, and water-oriented wildlife. What are the nutrient-related impacts and what do we need to protect against? The science panel, and you'll see here, we focus mainly on fish. So part of the technical support document is evaluating exceedances of dissolved oxygen and pH that are relevant to early life stages and other life stages as well. So here's an example graph on the right-hand side where we're seeing daily minimum dissolved oxygen, our threshold of 5 for early life stages. We're seeing that exceeded at lower dissolved oxygen concentrations and in Provo Bay in some cases. There's also a great report coming out of SOMAS and SWCA that they evaluated the requirements for spawning and rearing for different fish species and the percent of time those conditions were met. So I've included just a portion of that table here. This was assessed with medium confidence from the science panel. I think we're going to save questions about this till the end, so I'll just keep moving. Here's a question question 4 relates to future conditions of the lake. And then I will go through each of these questions individually. Just to note here, there's ongoing and upcoming work that's informing these questions. So confidence statements were not generated for these, so you won't see a statement about confidence. So what would be the nutrient regime of Utah Lake under no human sources of nutrients? The science panel came to the conclusion that Utah Lake is expected to be less eutrophic than it is today under conditions of minimal nutrient loading. A lot of that was generated from evidence from those paleolimnological studies showing that the nutrient concentrations were lower. Algal communities were dominated by those less nutrient tolerant species, and we also didn't have any observed abundance of cyanobacteria. Also, we know that the historical water clarity was higher and macrophyte cover was greater. One other thing to note is just that the mass balance modeling and the mechanistic modeling efforts, these will also be used to infer those reference conditions or those minimal nutrient regime conditions for Utah Lake. The second sub-question here is, would nutrient reduction support a macrophyte dominated state? The science panel came to the conclusion that nutrient reduction alone would not be sufficient to restore macrophytes. It has to be done in combination with these other active management strategies that you see on screen. Nutrient reduction is one of those levers that we can pull, but there's also more active restoration efforts that are needed alongside that. We also know that lake level fluctuations are a significant barrier, although they're not something that we can necessarily directly manage as some of these things are, but they definitely are a factor in supporting macrophyte recovery. And then the final question as part of question 4 is, to what extent can the magnitude, frequency, and extent of harmful algal blooms be reduced through nutrient reductions? So part 1 of the answer to this question relates to linking the impacts of nutrients and harmful algal blooms. We have those nutrient bioassay experiments, stressor response analysis demonstrating those empirical relationships between nutrients and HABs, like you see on the right-hand side here. We have the paleo analysis, and then we also have evidence from the literature that links nutrients and harmful algal blooms. So those are all of the linkages that we've made between nutrients and HABs, and then there's also ongoing work through the mass balance analysis, the analyses for the technical support document, as well as the implementation planning that the steering committee is doing to actually evaluate the magnitude, frequency, and extent of harmful algal blooms and how that might be impacted. So thanks for sticking with me and going through that. Again, you'll all have an opportunity to think about how you'd like to dive in on any of those questions if you want to hear more. Otherwise, I'll pass it over to Heather and Samuel to see if there's any time for questions right now.
Fantastic. I think we have time for one steering committee member question if we have one at this time. Otherwise, we can pause. Rich, go ahead.
I had several questions. One, a comment. We have all those studies that were sponsored by the Water Quality Board and so forth. When you're going through these, can you comment of when these studies that were done were related to this? Do you know what I'm saying on that? No, you don't know. Okay, well, skip that one. The next question I had was on the effects of lag time on the chart that you had. I was just wondering if they took into effect the last 2 years where there was significant of water exchange in the lake, if they took those into account and say how that affects that lag time. Do you understand what I'm asking on that question?
Mhm. Yes. Yeah. So the question relates to how much of the most recent 2 years of data were used to evaluate the lag time. A lot of the evidence for discussing the lag time response related to those sediment batch sorption experiments, which were irrespective of the water column concentrations or conditions specifically. And then also the mass balance analysis was used over an averaging period of years. So yes and no, there's some of that is inherent in evaluating that variability, but also some of the evaluation was done in the absence of specific years of context. And then, Rich, maybe to your first point, I've highlighted just a few of the visualizations here in this presentation, but we do have a full literature cited section in the report that you can reference that references where each piece of evidence came from for each question.
Awesome. Thanks, Kateri. Heidi, go ahead real quick.
Thank you. Can you hear me?
Yes.
Okay, great. I've got 2 questions as well. One is regarding the flushing, the natural flushing that happens of Utah Lake, depending on its the hydrologic cycle each year. On higher or wetter years, is the phosphorus transport downstream of concern relative to the health of Jordan River and ultimately Great Salt Lake. Just wondering if somebody can speak to that.
Whether phosphorus concentrations are higher going downstream in wetter or drier years.
Yeah, you were talking about the load, that it's kind of equalized if it can flush, if flushing is part of the model, that's good for the Utah Lake, but is that also good, is basically my question, for Jordan River and Great Salt Lake, or the wetlands of Great Salt Lake?
Looks like,
right. Yeah, does Mitch have an answer to that?
Mitch, go ahead.
Yeah, I was going to say, going back to the Jordan River dissolved oxygen TMDL, Utah Lake was identified as a source of nutrients contributing to eutrophication. So any improvements to Utah Lake is going to improve Jordan River, which will improve water quality in the downstream wetlands. So yes.
Heidi, go ahead. Did you have another part of your question? Hold on. How about now?
How about now?
Okay.
We're good? Okay. Yep. So talking about the inclusion of active management in addition to nutrient management, nutrient level inputs, is it possible that things like planting, increasing the cover of the macrophytes in the lake could negate the need to lower the nutrient inputs?
I think in certain locations that might be possible, but at least Leighton King's work demonstrated that reducing phytoplankton and the light shading that comes from phytoplankton is a part of that restoration procedure, at least in the deeper areas of the lake.
Yeah, I'm just thinking in time, once you establish an actual community and extensive communities of macrophytes, it could cause a shift in more clear water and lower phytoplankton and so forth. But anyway, just curious. Thank you.
Yeah, lots of interacting drivers for sure. And I'm maybe not the best person to speak on that specific.
Darren, you got one sentence. We do need to take a break here to move on, but go ahead.
One sentence. So in the work that mostly David Richards is working on, you know, if we restored the macrophytes to where they probably were pre-settlement times, it would be a huge additional reservoir for nutrient storage. And so I believe the answer would be yes, it could lower water column values because it would represent currently unused or potential nutrient storage compartment in the modeling.
Thanks. All right. You might have more questions, steering committee members, and we would love to give you time to visit with each other and with the science panel about that at a time that is not this. And therefore, wanted to give you a quick opportunity to respond to the poll that just popped up on your screen, where you may indicate what charge question topics are you interested in taking a deeper dive into at future steering committee meetings. You can select as many as apply. Once you have indicated your response, you may take a quick break. I do want to start as close to 2:20 Mountain Time as we can, so we don't shortchange our atmospheric deposition conversation. So pop in your responses when you're ready, and then take a break, and we'll come back at 2:20. Rich, do you have a question while we're transitioning?
It's not letting me vote on that. You might have to
Samuel?
kick me out or something.
Well, that doesn't seem nice. Samuel, technical difficulties, maybe you want to restart that?
Yeah, let me take a look. Oh, what's going on here?
Oh, Sarah says the poll says hosts and panelists cannot vote.
Okay.
Allow panelists to vote. Hold on, I just turned it on. Okay, how about now? Rich, can you do
Now
it
I
now?
don't have any questions. Now the survey is not up for me.
Okay.
Fun.
Okay.
Technical difficulties. How about now?
I can see the survey, but can't vote still.
All right.
I'm the only one that has this trouble. How come I'm always the trouble child?
You're the only one who said it out loud. I bet you're not the only one who's having the issue. So allow panelists to vote. I just turned that on. Now, do you still see it and have answers? And can you answer, Rich?
I don't see the survey, so I can't check it yet.
All right.
Okay.
Still same problem.
Okay. Take a 5-minute break. Come back at 2:23, and Samuel will have this sorted out in some way, shape, or form, and we will transition at that time also to our AD conversation. Apologies for the technical difficulties. Zoom is full of exciting fun and surprises. All right, it looks like Samuel has figured out that we can't solve on the fly whatever the polling problem is, but if you hover over the charge question poll, the QR code with your phone, you should be able to link to the poll. If that is way more technology than you feel like dealing with, and you just want to put in the chat which items on the poll you would like to talk more about, we will track it that way as well. We thought we outsmarted Zoom today, but it doesn't look like we did. The house always wins. As you're working on that, would love for folks to start to come back so we can get a jump here as soon as possible on our atmospheric deposition conversation, because there's a lot there. I'd hate for you to miss any of the juicy bits. I do see responses coming in now into the poll. It sounds like maybe that QR code is working for folks. And again, if the QR code isn't for you, feel free to drop your preferences for future conversations into the chat. Thank you. We got a future conditions from Brad. Samuel, you'll start tabulating things that pop up in the chat, yeah?
Yes.
All right. Here come all the lovelies. Hello, lovelies. Cool. While folks are working on that, we'll leave the code up for what, 1 more minute. The code's going to come down. So if that's your gateway, make sure you click on that. Again, you turn on your camera on your phone and you hover the camera over the QR code, and then you get a little link, and then you click on that. We got a Habs in the chat. Thanks, Hans. All right. While that is happening, we will go ahead and move on. Now it's 2:25. Samuel, if you go ahead and take down the QR code and pop back up the slides so we can transition to our atmospheric deposition conversation. Craig, I see your thought there in the chat. Thank you ever so. Again, folks, keep putting those in there if you're not able to access the poll. Outsmarted by the technology once again. Samuel?
All right.
All right. This is atmospheric deposition, darlings, and it is a whopper of a conversation. The science panel has spent a tremendous amount of time talking about this. And as you may already know, particularly if you were with us this summer, there are 2 perspectives that inform the final outcome on the atmospheric deposition. We had a majority group who came to the final conclusion, and then there was a minority perspective. We think it's really important for you to understand both the majority perspective and the minority perspective. And so what we're going to do now is a fun transition of 3 presentations. Thing 1 will be Samuel, and he will talk for 20 minutes. And then Mike Brett will talk about the majority perspective for 20 minutes. And then Theron will talk about the minority perspective for 20 minutes. You probably have noticed that I am stressing 20 minutes. Here's the haps. Each one of our presenters will have exactly 20 minutes to give their presentation. There will be a timer that's going to pop up in my window for a 20-minute countdown that everyone will be able to see. So we'll all know that I'm treating everyone fairly. So each presenter gets 20 minutes of uninterrupted speaking. That means ain't nobody going to jump in to assist or counter speak or whatever. And we're all going to have our very respectful faces on. Then at the end of the 20 minutes, I will expect each of our speakers to complete your thoughts. You may complete your sentence, but not your paragraph. I would be really loath to have to mute you if you kept talking. So please don't. 20 minutes is a lot of time. Try to get there if you can. I have told the speakers that they don't have to talk about everything on their slides, and you as steering committee members can ask them to go back, and that will help them stay within their 20-minute time frames. We're going to go through all 3 presentations before we get to any of your questions. So if you have questions in the intervening period, please go ahead and jot those down. You can pop those in the chat. I do feel compelled to remind every single one of us about sometimes tempers run a little hot on this topic. And it is okay for professionals and experts to disagree on methods and outcomes. I will expect all of our speakers, both from the science panel and from the steering committee, to treat every single person in this room, and not in this room, but part of this process, with respect in the way that you talk about them, their expertise and their approach. Okay to disagree, but there's no need to be unpleasant about it. So that's all I have. Samuel, if you want to show me your main slide, I will start your timer, darling, because the rules apply to you too, don't they?
Yes, they do. So thanks, Heather, for the tee up. Just kind of a quick overview of the presentation outline. What I'm going to present here is an overview of the atmospheric deposition subgroup process. I'm really just here to kind of say what happened step by step and what were the decisions made, when were those decisions consensus and not consensus. And that's when we will turn it over to Mike and Theron to give their presentations respectively on the majority and minority perspectives. There are a couple key decisions that there were diverging perspectives on. That is whether to consider insects as contamination and discussions on attenuation of atmospheric deposition over Utah Lake and its relationship to Bird Island data. So I kind of wanted to flag those two topics before I get into it, so you all can kind of pay attention to those when they come up. But really, I'm just going to talk about the step-by-step process and then turn it over to Mike and Theron to give their perspectives. So just a really brief background on the atmospheric deposition timeline. This conversation began with the science panel in October 2019. Science panel member Dr. Janice Branney writes the white paper estimating total and bioavailable nutrient loading to Utah Lake from the atmospheric, which the science panel discussed. In December 2019, the science panel approves temporary atmospheric deposition loading rate recommendations while additional research is conducted. In April of 2019, the Wasatch Front Water Quality Council submits a proposal to measure atmospheric deposition in Utah Lake with input from the National Atmospheric Deposition Program. The science panel provides recommendations on that sampling plan. And I now realize that April comes before October and December, so please ignore that. But that leads us to May 2020. The science panel provides recommendations to the Wasatch Front Quality Water Council Atmospheric Deposition Program. And the science panel also provides an update to the steering committee on engaging with all potential sources of information and developed a memo talking about that engagement. So over the years, Wasatch Front Water Quality Council conducted their atmospheric deposition research. And in April to August of 2022, science panel members come together to discuss atmospheric deposition rates, and the science panel decides to form a subgroup to discuss assumptions, aggregate available data, and discuss atmospheric deposition results. So why did the subgroup form in the first place? The in-lake nutrient water quality model that's being developed by Tetra Tech requires a numeric input for nitrogen and phosphorus atmospheric deposition rates. So it was important for the science panel to come up with a recommendation on a numeric value for atmospheric deposition for the purposes of developing and calibrating the nutrient model, which is the reason that this subgroup needed to form in the first place. The members included Dr. Mike Brett from University of Washington, Dr. Mitch Hogsett, Dr. Theron Miller from Wasatch Front Water Quality Council, and Dr. Hans Pearl from University of North Carolina. This subgroup met a number of times, 20 times from August 18th to 2022 to February 23rd, 2023. Subgroup objectives were to analyze the available information and data to improve understanding of atmospheric deposition to Utah Lake, work collaboratively toward a recommendation for atmospheric loading, ideally achieved through consensus, and along the way document the science panel's decision-making process for analyzing and evaluating evidence, which if you had a chance to take a look at the report, we did our best to track the decisions as well as when those decisions were consensus and when they weren't as part of this third bullet. Just as kind of a really quick overview, the subgroup had several tasks. The first was to develop and agree upon an analysis plan. Then their next step was to review and summarize raw data, which I'll talk about in just a second, from Gus Williams and Wood Miller data sets, evaluate outlier samples and quotes for potential explanations, evaluate spatial interpolation among sites and attenuation of fluxes, evaluate speciation, compare direct estimates of atmospheric deposition to other constraining analysis. Then lastly, determine loading for inclusion in the Utah Lake nutrient model. Lots of steps, lots of things to cover, but this group worked hard to walk through these different steps as a subgroup. So just kind of taking a look at what that first step was is to review and summarize data. So there were several data sets that the subgroup used. The first is what is referred to as the Williams data set. This came from 3 different studies, but in 2021 were combined by Dr. Gus Williams at BYU and Seth Barris into one data set. So you can see here that spans from 2017 to 2020 and probably will just be referred to as one data set known as the Williams data set for the rest of this presentation. It also, there was an additional data set collected by Wood Miller, Dr. Wood Miller from 2017 to 2020. And these were the two data sets that the subgroup explored and summarized. And maybe something worth note that's not on this slide right now, but it will come up in conversation is whether or not the data was screened. And it's important to note that the prior from 2017 to 2019, the Williams data was unscreened. And then in 2020, the data is partially screened for part of that year, which will come up as part of the subgroup conversations later on. So if people can take a quick note of that, as well as you can see in this column here when there was metadata available, which I will talk about later. But you can see metadata available for the Williams data set in 2017, the Williams data set in 2020, and not available for these other years. So this one is the first steps it took to summarize the data. The subgroup had consensus decision on this, but essentially there were some non-detect values in the Williams data set that the subgroup agreed to list as 0 milligrams over meter squared. There were very few values listed, so it was estimated that this wouldn't have a big impact on the outcomes of the data. And then another early on agreement was the Wood Miller data set was in a different metric than the Gus Williams data set. So we had to do some conversion of some of the measurements to make sure all of the measurements between the two data sets have the same units. And we did that by taking the Wood Miller data set and assigning precipitation values based on the nearest precipitation gauge. I won't get too much into the details, but essentially what this did was put all the data into one unit so it was comparable across the two different data sets. So just as a really quick visualization, this is what the data sets look like after they were processed. You can see here on the y-axis that they do have the same units now due to some of those early conversion. And you can see the way that this data is plotted. And this is for the total phosphorus and soluble reactive phosphorus time series. And then similarly, plots were made for that's then dissolved inorganic nitrogen. So this was the first step, and the subgroup came to some consensus decisions. The next step was to take a look at outliers and the data sets a little bit more in depth. So the first thing that the subgroup did was identify what's the method for for identifying quote unquote outliers. The first thing that they did was use this method, which is taking the 75th percentile of the data and adding 1.5 times the interquartile range, which essentially showed where there were outliers by this definition within the data set. You can take a look at the data set here. I believe this is Gus Williams total phosphorus, but the purple are the data points that aren't considered outliers, and then the orange were the data sets that were considered outliers. Maybe an important thing here to note is that these outliers, it was just an exploratory process. So these outliers it's not like they were removed. This was just to get a better understanding of which which samples would be considered outliers according to this methodology. And it was used simply to identify those high deposition events, not remove the data. The subgroup talked about potential explanations for those high outliers. Potential explanations included weather events, local deposition sources, or contamination. And so the subgroup members agreed to use this interquartile approach to identify those distributions so that they could discuss it further as it relates to these possible explanations of weather events, local deposition sources, and contamination. So this is where we had the first decision point where there were disagreements within the subgroup. And this is whether or not insects should be considered atmospheric deposition, legitimate sources of atmospheric deposition, or contamination. 3 subgroup members agreed that the insects in sampling buckets should be considered contamination, and 1 subgroup member did not support this decision. I won't get too much into the reasoning behind that because that will be a part of our majority and minority perspectives to come after my presentation. So, but this was one of the first places where we didn't have consensus decision-making on the process. But this did have an impact on the data set itself. If we, insofar as insects are considered contamination, subgroup members discussed what that means for interpreting the data. And they supported including data collected from screen samplers with the screens being in place, which would mean that insects and other sources of contamination, quote unquote, would not be able to get into the samplers. And then also data where metadata indicated the samples did not contain insects. Data from unscreened samplers without metadata or where metadata indicated that insects were present in the sample were not used. And so if you take a look at the data sets that were available, these 3 data sets, Williams in 2018, Williams in 2019, and the Wood-Miller data did not have the metadata available. And so according to this kind of decision outline, were not used in the analysis for the rest of this process. The Williams 2017 data and the Williams 2020 data did have metadata available, as well as the Williams data I think in May of 2020 were screened. And so the subgroup took a look into that data set, and where the metadata indicated that insects weren't available, those samples were included within the entire data set. I'll go through this a little bit quicker, but essentially when you remove data points from a data set, you need to fill in some of those gaps if we want to calculate a cumulative annual load. So the subgroup discussed how to fill in those data gaps. That included a couple of different options, but ultimately the subgroup conducted an analysis where they compared the data, the fluxes with weather events to see if there were any statistical relationships, and then use those statistical relationships with different weather metrics to fill in those data gaps. Essentially, this is the preferred option because it is assumed that atmospheric deposition is episodic and that it's tied to different weather patterns. So storms and things like that might bring in more atmospheric deposition. So tying it to weather helps fill in those gaps in a way that is statistically relevant. So moving through the Miller data set, all the previous conversation that I had on the metadata and everything like that applied to the Williams data set. The Miller data set, the subgroup handled a little bit differently. Just a quick look at the two different fluxes from the Wood-Miller data set and the Williams data set. The first is that total phosphorus and dissolved inorganic nitrogen fluxes were significantly lower in the Wood-Miller data set than the Williams data set. So you can take a look here. The purple are the Wood-Miller fluxes by site, and the Williams you can see in the orange, and you can see them side by side when sampling equipment was at both locations. So I'll go through this one, but essentially the subgroup members agreed to primarily use the Williams dataset as the primary line of evidence for calculating load to Utah Lake. We discussed the Wood-Miller dataset for quite a bit and discussed different ways, different potential sampling methods that might impact either increased fluxes or decreased fluxes. That included potential evaporation from sampling tubes, overflow from funnel-shaped collectors if precipitation events were greater than 0.5 inches, the loss of dry deposition blowing off from some of the shallow pan collectors, and then maybe some inconsistent sampler cleaning. Because of these different potential impacts to the data, the subgroup decided to focus particularly on the Wood-Miller dataset for collecting loads. And maybe also note is that the Wood-Miller used modified precipitation samplers and not atmospheric deposition specific samplers for the study. The Williams dataset did use the atmospheric deposition specific samplers. So shoreline fluxes and attenuation rates, this was the next step of trying to figure out what potential fluxes are from the shoreline and how they may attenuate over Utah Lake. Before this subgroup, previous studies had assumed some flux decrease away, moving away from the shore. The Wasatch Front Water Quality Council installed a sampler on Bird Island to quantify potential attenuation. Essentially, this sampler, which you see down here, the idea was that if Bird Island fluxes were lower than the shoreline fluxes, that would show that attenuation does occur, moving away from the shore. If the Bird Island fluxes were equivalent to shoreline fluxes, this would indicate that attenuation does not occur. What the subgroup found is that the Bird Island fluxes were significantly higher than the shoreline fluxes, so they had to develop some alternative hypotheses. The first being that if the Bird Island fluxes were higher than the shoreline fluxes, that might indicate that there's a higher land-based flux not captured by the current sampling array. If the Bird Island fluxes were higher than the shoreline fluxes, another hypothesis was that the lake-based source of deposition, there might be some lake-based source of deposition to the Bird Island sampler, like bird droppings, aerosolized materials, and lake spray. This was not, the subgroup members decided to not use the Bird Island data because they could not rule out the hypothesis that lake-based sources of deposition could be impacting the Bird Island samples. One subgroup member did not support this decision, and you will hear perspectives from that later in this presentation. I will go through this one pretty quickly because I see I have 3 minutes and 40 seconds left, but these are attenuation. Things for the steering committee to know is that there are both regional and local sources of atmospheric deposition to Utah Lake. The samplers collect both local and regional deposition. So it is needed, so independent estimates for both local and regional deposition were needed. When it came to estimating local sources, the subgroup discussed using some studies, the first being from Van Kuren et al., which showed how different grain sizes attenuate over the lake, noting that local large particles are expected to attenuate while small regional particles don't. And then they used dust grain sizes from a Utah Lake focus study, Goodman et al., to take a closer look at those attenuation rates. Dr. Mike Fred is going to talk a lot more about this during his presentation. And then the other was to estimate regional sources. We had a couple of studies which had sampled materials which estimated that 91% of urban dust was regional, and then estimated the phosphorus content, and you can see these regional fluxes and dissolved inorganic fluxes. So essentially what the subgroup discussed was that when and how to apply attenuation rate to shoreline sampler fluxes, and 3 subgroup members supported applying an attenuation rate to those shoreline samplers and applying a regional flux rate beyond the attenuation distance. I'll talk about what that means in just a second. And then 1 subgroup member did not support attenuation and cited the Bird Island fluxes as evidence that attenuation is not occurring on the lake, which we will hear about later in this presentation. So essentially what this group did once they had talked about attenuation is you see the 4 sampling sites from the Wood Miller. They put the data into GIS and then essentially map out a gradient of the fluxes based off the cumulative annual load from each of these. And so you can see where there might be greater atmospheric deposition and not. And then what they did is assign decay rate under several different scenarios, 100 meters of attenuation, 200 meters, and 2,000 meters, as identified in literature, which will be talked about in just a bit. But you can see the way that that is shown here, that the fluxes attenuate into the lake. And then in the middle of this area is the regional flux, which is applied to the entire lake, since the regional fluxes don't attenuate and are would then be deposited across the entire lake. And we also ran one scenario that assumes no attenuation to see what that value would look like with the approved data set. So Really quickly, the attenuation rates by the analyses, these first 4 rows show the attenuation of the approved data set. If we assume attenuation of shoreline samplers at 100 meters, we get 31 metric tons of phosphorus, dissolved inorganic nitrogen at 218. If you assume no attenuation, you can see that that number goes up to 93 and 351 respectively, and then all the numbers in between. This is just from the subgroups work. And the data set that they approved for the analysis. And you can see the other studies here. And then really quickly, the load recommendations from the subgroup were 32 metric tons with a range of 31 to 45. This was not a consensus decision, and we had one subgroup member recommend a higher amount at 150 metric tons of total phosphorus with a range of 93 to 200. And then they talked about chemical speciation, but there was general consensus.
Oh, that was a nice summary of that there. I was like, oh, I'm going to have to like zip ya. Okay, cool. Whew. If anyone is wondering, 20 minutes feels like a long time until it doesn't. Samuel, well done. Thank you very much. Next will be Mike Brett. Mike, as soon as I see your slide pop up there, we should start your timer. And let me make sure that you can unmute. All right. Ready to go? Yep.
Okay, great. So I've already been introduced, but one thing I'd like to point out is that I have served on the science panel for over 6 years. So I've had a lot of time to get to know about your lake. So the main steps of the AD decision support analysis was to review the data, to come up with explanations for some of the extreme values in the data set, to explore the question of potential attenuation, to look at the speciation of the nutrients, to compare direct estimates to other estimates determined from other places, and to come up with a final estimate of AD loading to Utah Lake. And I think most importantly, to have a transparent process where you could actually see how the sausage was made, so to speak. I have my outline for today are the points that we agree on. We're going to talk a lot about what we didn't agree on, but there are points that we agreed on. I'm going to talk about how the AD data was vetted, and then about AD attenuation first principles, and whether Bird Island is a representative site for AD sampling. And I'm going to talk about a reality check that was suggested by David Gay, and I worked out the data for that, some other constraining estimates, and then perhaps that does be my main points there. So these are the points that we agreed on. I guess I won't spend a whole lot of time talking about these, but the point I want to make here is that there were a lot of times that we actually agreed. And so today we're probably, well, we're going to be very focused on the times when we disagreed, but we did agree about half the time on the main points. And I think that's an important thing to note. The decision tree that was used to decide which samples would be included in our analysis was the sample screened or not? If the sample was screened, we used it. And that was because if it was screened, then we believed that it was very unlikely to have been contaminated. If it wasn't screened, then we asked, was metadata available? If metadata was not available, then it was not used. If metadata was available, then we asked, was the sample contaminated or not? If the sample was contaminated, it was not used. If the sample was not contaminated, it was used. So basically, if a sample was screened, it was used. If a sample was unscreened and metadata indicated that the sample was not contaminated, it was used. If a sample was unscreened and metadata was not available, it was not used. And if it was unscreened and metadata indicated the sample was contaminated, it was not used. We used the same process for nitrogen and phosphorus samples, and we did not look at how this, decision tree affected the final estimates as we did it. We just had a philosophical approach to which samples we had the most confidence in and which ones that we were less confident in. This is showing, some of the estimates that you would get based on the median of the data, the geomean of the data, the mean of the data for the samples that were not contaminated, the samples that lacked metadata, and the samples that were known to be contaminated. And the point that I want to make here is that there was a small number of samples that had extremely high values. And so these particular ones I've circled here, there were, in particular, 6 samples that were collected from Saratoga Springs in the summer of 2017 that had tremendously high values compared to all the others. And these samples were said to be contaminated with sweat bees. And the average for these 6 samples was 800 times higher than the median for the uncontaminated samples. And just removing these 6 samples from the overall data set reduced the estimated AD loading by 50%. So the issue with contamination is that some of the samples had values that were many orders of magnitude higher than the others. And these samples were reported to have been contaminated with sweat bees. And I want to note that the way that people that sample, pollinating insects, related bees or even sweat bees, the way that those are actually collected is very similar to the design of the AD collectors that these organisms were found in. And in fact, Barris et al. Showed a nice figure here showing one of their AD samplers contaminated with these sweat bees, and they said that they were collecting about 100 of these every 2 days in their samplers. And so there were a lot of these bees that were attracted to the samplers. And they recommended in their study not to use screens to keep the bugs out of the samplers because they weren't getting any bees in the samplers that had to screen. So the majority recommendation on with regard to insects was to not use insect contaminated samples for AD, the overall AD estimate. We recognize that insects do fall into lakes. I have this little graphic up here of a trout fly because I'm an avid trout fisherman, an avid fly fisherman, and I have caught many trout in my life using imitations of terrestrial insects. So terrestrial insects do fall into streams, they do fall into lakes. But aquatic insects come out of lakes as well. And so it's a complex question. And the sampling design that was used for the AD study is not an appropriate sampling design to get at the influx and efflux of insects from Utah Lake. That would require a dedicated study to get at that because there are insects coming out of the lake and there are insects going into the lake. In terms of AD attenuation first principles, this is a figure I made from some of the data presented in the Gus Williams memo. And the point that this figure makes is that the particle settling velocity in the atmosphere is geometrically related to the size of the particle. So if a particle is 10 times larger, it settles approximately 20 or 30 times faster. So there's a very strong relationship between particle settling and particle size. And large particles will settle very rapidly. Small particles will stay suspended in the atmosphere due to Brownian motion, which is just a random vibration of molecules. These are some of the studies that we consulted when trying to calculate AD attenuation in Utah Lake. And this shows here that the small particles in a study at Lake Tahoe transport, the large particles attenuate. So the large particles fall out, the small particles stay in the atmosphere. And it's very well established that particle transport is related to particle size. There have been related studies on Tahoe showing that there's about 23% attenuation of phosphorus in dry deposition and about 89% attenuation in wet deposition. So the first principles for attenuation are how large are the particles and how far will particles of a particular size transport. We have, data from Tahoe showing how far particles of particular sizes transport, and we have data from the Utah Lake Basin looking at the size distribution of dust particles that were collected there. So we have size and we have transport with size, and using those two and an assumption for the background regional deposition, we can calculate how much small size particles and how much large size particles are attenuating in Utah Lake Basin. So one of the big questions that we had for Utah Lake was, we spent a lot of time discussing whether Bird Island was an appropriate site for sampling. And one of the, critiques of the majority opinion was based on whether there are a lot of birds at Bird Island. And there's a quotation here that says thousands and thousands of birds on Bird Island was claimed by one of the panel members. I'm pretty sure that that was something that I said. And I have a little video here of Bird Island showing the birds there. So I believe very strongly, and I think the other panelists believe very strongly, that Bird Island is a bird rookery. I don't know about thousands and thousands of birds because I don't think anybody's actually conducted a census of birds on Bird Island, but it is a rookery. And so one of our concerns is that there's much higher phosphorus loading estimated for Bird Island than for the shoreline sites, and why would this be the case? And one of the concerns is obviously that this is related to the fact that it is a rookery. And so one of the points I want to make is that the birds don't actually have to leave their droppings directly inside of a sampler. They just have to be in the vicinity, because there's, in any organisms, there's little bits and pieces shedding off. I read somewhere that a substantial part of dust in homes is just skin cells. Something like maybe 10–20% of the dust in your house is just skin cells that are shed from your body. So having a lot of organisms, a lot of living animals close to a sampler means that there's got a lot of material floating around. One thing that I want to point out is that it's often been claimed that the AD at Bird Island is not any different than the shoreline samplers, but in fact, it's about 3 times higher for the data that's been collected. So these are the cumulative estimates. So the cumulative estimate of AD at Bird Island is about 3 times higher. And from a mass balance, this is not possible if Bird Island is simply a function of the shoreline sampling. You can't have 3 times more than your source. And I did a statistical analysis on this using a paired t-test, and it's not significant at the classic 0.05 level, but the sample size is extremely small. So our statistical power is very weak. But I think it's very plausible that the high phosphorus concentrations observed at the Bird Island site are due to the fact that it's a bird rookery. And I also want to point out that this Bird Island inclusion or exclusion only relates to this difference between the various attenuation scenarios. So if we have no attenuation, then we estimate 3 times more loading to the lake than if we have the attenuation based on the particle sizes. I also did something called the David Gay reality check. And what David Gay suggested is that we compare the estimates from the National Acid Deposition Modeling process to the estimates that we were getting from our field sampling. And he estimated, based on the National Acid Deposition Modeling, that there should be about 384 tons of nitrogen loaded to Utah Lake each year. And so we compared that to our numbers, and our numbers came up with 351 metric tons per year. And I think this is a pretty good match because the EPA model doesn't account for attenuation of dry matter, and DIN is only, it's not the entire TN loading. So I think the match between 384 and 351 is pretty strong. He also suggested that if you have a good estimate for TN loading, and if you have a good estimate for the nitrogen to phosphorus ratio of the deposition, then you could also back calculate TN deposition, TP deposition using that ratio approach. And so he came up with, as I said, 384 tons for TN. And he suggests that we come up with a ratio for TN for nitrogen to phosphorus, and then back calculate TP using that ratio. And so I calculated the ratio for all of the data that we had available for AD. The mean central tendency for all these data was about 7.5 TN mass per TP mass. And if I apply that to our estimates and compare them to the David Gay estimate, I find that in most cases, they match up really well, except that the David Gay approach, which is taking the TN estimate and multiplying it by a TN to TP ratio, is a little bit lower than what we came up with. So the David Gay reality check matches up with what we did very well. The other thing that we did in terms of, trying to constrain our estimates, one thing that I've been working on quite a bit, because I've been doing the mass balance for phosphorus in Utah Lake, is one of the things that we can look at is how much phosphorus accumulates in the sediments of Utah Lake each year, and how does that match up with known external inputs from tributaries, from wastewater treatment plants, groundwater, and then how much that would match up, how well that would match up for various atmospheric deposition scenarios. So it's a simple equation. If we know how much sediments accumulate in the lake of Utah Lake each year, and if we know the dry mass to wet volume conversion, and if we know the sediment mass to dry mass conversion, and if we know the surface area of Utah Lake, we can calculate how many tons of phosphorus accumulate in the sediments of Utah Lake each year. And so we need to know, how much sediment accumulates. How much sediment accumulates in Utah Lake is poorly constrained. We need to know the dry to the wet to dry mass conversion. That's well constrained. We have lots of data, and it seems to have a fairly well constrained distribution. And we need to know the sediment phosphorus content in Utah Lake, and that's also well constrained. And we can take these three numbers in the surface area of Utah Lake, and we can calculate how much phosphorus accumulates in Utah Lake based on actual observed deposition in Utah Lake. And we come up with this distribution. You can see it's very skewed because one of the estimates for phosphorus, for sediment accumulation in Utah Lake was significantly higher than the other. So there was 5 low estimates and 1 high estimate. But we can match this up with different AD scenarios. And if we match it up, the 32 metric tons estimate that came out of the consensus document, the majority perspective, matches up with basically the mode of this in about the 45th percentile of this distribution of estimates. The Williams 150 tons per year AD estimate matches up with about the 76th percentile, and the Williams 250 tons of AD per year matches up with the 83rd percentile, which basically says that the Williams estimates are plausible if we take that one much higher sediment accumulation rate, but not very plausible if we take the 5 low sediment accumulation rates. Another constraining estimate was a memo prepared by Greg Carling titled Atmospheric Deposition of Total Phosphorus to Utah Lake. And in this, Professor Carling estimated deposition to Utah Lake based on a round dust deposition loading of 30 grams per meter squared per year, and based on his 4 samples that indicated that urban dust collected on a BYU campus had about 5 grams of TP per kilogram of dry matter. And using these 2 assumed values, he calculated about 57 metric tons of TP per year is loaded to Utah Lake. But Carling also estimated that the playa dust has a phosphorus content of about 2 grams per kilogram of dry weight. And it's commonly argued that the long-term regional contribution of AD to Utah Lake comes from playa dust. And the playa dust that was measured by Carling has Utah's phosphorus content of about 2 grams per kilogram. And if you take that concentration, the playa dust of phosphorus concentration, and apply that to the 30 grams per meter squared per year of deposition, this would substantially lower the Carling estimate. So the Carling estimate is, the 57 tons is very dependent upon the high phosphorus concentration in urban dust. And I think that's the last slide I want to do. I'm going to stop right there. So I'm actually going to stop 1 minute and 30 seconds early.
Well, aren't you just the teacher's pet? Well done, sir. Thank you very much. Sadly, that extra time does not accrue to anybody else. So while Mike takes down his slides and Theron gets his up, I will get my little timer restarted. And folks who are observing, if you're wondering why we're doing the 20-minute timers, it's to make sure we save time for your questions and discussion. Theron, you want to get those slides up, darling? Oh, I better probably unmute you too, huh? Can't talk if you don't unmute the man. Nope, that was the wrong one. Hold on. There we go. Okay, there, you should be able to unmute now, yeah? Okay, and then get those into slide mode and away we shall go. Aha, all right, take it away.
Okay, so you can hear me okay?
Yep.
Okay, so clearly we have a difference of opinion on this stuff. And so I'm going to have a hard time trying to get all my information into 20 minutes, but I'm going to try real hard because I'm going to try to explain why some of these conclusions were not really as legitimate as they appear. Okay, so this again becomes the root of why we have these disagreements. Also, I am the lone dissenting, they talk about the opposing opinion or the minority. That's just me. So you could call me the lone wolf, but I'd rather think that I'm the lone ranger trying to come to the rescue of this data. So anyway, we all know that this is the original issues that we have with attenuation and contamination and outliers. So I'm going to start by just a review of Jacob Olson's and Seth Barris publications, just to show how wide these numbers were. Particularly Jacob's data was ranged from 8 to 350 tons per year on the lake. So it looks like, wow, this is a huge range, and it literally was the way you treat the outlier, what you choose to be outlier data or not. Okay. The Barris data, again, this was 2 years of 2019 and 2020. The 2019 data had no screens on. This was the estimate. However, contrary to what the supporting document said, they did take out outliers. It's noted in the publication. Anything above 3 standard deviations was removed. So there's a number of samples, including that very high sample, 2 of them that were removed. The 133 is simply the screened data. Everything that was screened, except for maybe 2 or 3 sites before the May 20th, when he started sampling that had 1 high number, but the other 2 were not so far out of the range. So let me just move forward here a little bit. This is the map from the Jacob Olson's information. I want to focus on this Mosida site and the Saratoga Springs site that were both mentioned by Dr. Brett. So anyway, big note here. This Mosida site is located about a mile to a mile and a half of a very large 2,000 to 3,000 acre alfalfa farm. And this is the source of the bees, okay? The sampler itself in Mosida was located about 150 meters from the lake shore itself. And so if the bees are coming down from up here, and if they fell in the bucket down here, and by the way, this had many more bees than any other location, Saratoga Springs had some bugs in them that very likely came from the same source, over here and this farmland over here. But I'm submitting that if the bees came down here, yeah, they might be attracted to water, okay? But why would they simply want to stop at a 12-inch wide bucket when here's Utah Lake 150 miles away? So I disagree that they were seeking out the water from this bucket. Alternately, the southwest winds blow right in line from the farmland directly to the northeast and onto the lake water. Therefore, I also submit that if the bees were hitting the bucket, they were certainly hitting the lake surface. Okay? It was. Okay, and the same thing happened with some of the bees that hit Saratoga Springs, and there was not hundreds of bees every sample. There was one sample where he made an anecdotal comment, oh, that had to be over 100 bees. But when I looked at many of the samples, there was in the range of maybe 5 to 25. And they occurred during mostly May, a little bit into June, a little bit back into April. So most of the year, they were not contaminating the samples, other than maybe just the occasional 2 or 3 bees at a time. So I'm going to get into the attenuation question. This is kind of what Samuel mentioned, but this is out of, I believe, the Barris data as well. So you've noticed right away the sample at Saratoga Springs is missing, but this method of averaging a deposition over the lake is called inverse distance weighting, and it takes the relationship between any 2 or more of the samples and puts those in a relational organization, so that again, the southwest part of the lake had most of the accumulation. The northeast and the east part had less accumulation, so this showed overall less accumulation to the lake, and this reflects that. So we believe it's an accurate way of reflecting that you have accumulation going and deposition going across the lake, and not just attenuating back to a regional determined value. The alternate way that was used as decided on by the rest of the group was from the Van Kuren data, where literally the dark blue ring around here, I believe that's the 100 meter. The light blue line a little bit farther is the 2,000 meter. And again, as was mentioned, the rest of the interior of the lake went back to the regional deposition value. I believe, and our data suggests, that this is way underestimating the actual deposition on the lake surface. You saw this again, I discussed that. I'm going to talk about this. After all this controversy, we did decide to put screens in the buckets for the 2020 data for Seth Barris. 2 things happened. One is we did use pretty fine mesh. The mesh inside here is 500 micron. So if you include the mesh and the frame, it occupied about 65% of the area of the bucket that you could have samples or particles fall into. 65% was occupied by other material. Secondly, we found in literature that nylon has a electrostatic attraction for dust and clay particles. So there's actually, we believe, was an adhering to it, to the filament. So the result is that, and we actually did side-by-side comparisons, because samples on the east side of the lake didn't have bees, and so we put side-by-side comparisons with an NADP sampler alongside this design here for the summer, one over at Orem and one up on Farmington Bay out in front of Central Davis. And again, we carefully sampled every week. Our observations showed no bees in either sample on the screen or in the bucket in the NADP sampler. So there's lots of data which was removed, but let me back up one more bit here. Well, actually, I'll do it on the next slide, I believe. So they talked about the really high numbers for Saratoga Springs. And I'm going to talk about the dust that still could or couldn't go through the screens. So this is a picture by Jacob Olson, and I added, of course, the labels. So his sampler was just a quarter mile south of Saratoga Springs. There's a large gravel pit, okay, 1.6 miles to the nearest edge of the gravel pit. The shoreline was only 0.9 miles if you go to a northeast direction, which is again following the prevailing direction of the wind. If you go directly west or to the south, which happens when you have a frontal boundary come by, it's even closer to the lake. And literally, most of the samples from Saratoga Springs were tossed. Okay, they were tossed. But let me review what Jacob Olson wrote in his publication. It was literally this. Start right here. We believe the lower estimate bounds, okay, down to the 8 tons. It bounds the deposition rates because it excludes all loads from even dust samples, not just insect bodies, okay, and other legitimate sources of nutrients. So it identifies here that if it had even a particle of dust, that data set was removed and it was labeled as contaminated, okay? So that's the major source, and it's associated with wind events. And I want to talk just briefly about, let me go back one. This is the Van Kuren data. We saw this. Again, he used, it was Lake Tahoe, but he used dust particles that were mobilized from a nearby highway, mobilized by traffic, okay? He did a 100-meter transect perpendicular to the shoreline, and this highway was about 50 to 75 meters from the shoreline. And so, yes, particle size in this range here dropped out in 100 meters. Okay, all right. So that looks like justification to use that data for attenuation. He also discussed the data from Goodman and identified Greg Carling as a co-author. Okay, but here's the greater picture. They also collected dust samples from the West Desert, including the Severe Dry Lake, okay? And they collected samples from the top of the geology building at BYU, University of Utah, Weber State, and Utah State. These were the urban samples identified over here, okay? So what they found in these samples, as well as the fine playa dust samples, was the 10 to 20 micron diameter size. So you go, voila, well, okay. But then you got to ask yourself, oh, let me add one more thing. Also, the publication noted that with doing ICP and elemental analysis of the 26 elements, that these data here showed 90% similarity with the dust samples here based on elemental signatures. So what's the source of these samples? It's the West Desert, because there's no West Desert over here up in the Wasatch Range and in the Uinta Mountains. So how do you interpret this? They got 10 to 20 micron particles, and look at this scale here, about 180 to 250 kilometers away from the source. Only about 15,000 times the 100-meter distance that Van Kuren reported. There's a disconnect, a big disconnect in how to use that data and use this paper to justify that, oh, look how fast it fell according to Van Kuren. And this supports it. Yep, there's lots of dust that falls out in that dust particle size range, but it occurred 100 miles away plus. So there's a disconnect. What's the difference? I submit it's mostly the wind. Again, southwest to northeast pattern. Okay, I'm going to skip that. We saw that picture. I'm going to skip this as well because I've already discussed that. The third paper that they use is Wilson and Sear. This was a CAFO hog farm in North Carolina. In this, they literally were measuring ammonia, not even phosphorus, okay? And they said, oh, it falls back to background levels at 2,000 meters away from the source, okay? But here's their conclusion. As the distance between the human population increases from the industrial hog farm, the levels of ammonia decrease due to dispersion, mixing, and transformation. I don't see the word deposition in here, okay? So they admit it was dispersion. What does that look like schematically? I pulled this off the internet. So here's a point source off of a stack. As you are carried downwind, it disperses laterally. It did not attenuate due to deposition. It was natural dispersion, including the Brownian motion idea that occurs when you discharge from a point source, and if you have a source of wind. Okay, let's review the JASB data. Okay, they were also on Lake Tahoe with not with Van Kuren, because he did it before his study. They spent 9 years collecting this data. W-Well is the West Ward Lake side, right on the shoreline. There's a transect of 3 samples from buoys, and here what they call South Lake Tahoe. So here's the data on nitrate and ammonium. Okay, so let's talk about the Ward Lake, which is basically the shoreline or control. Mid Lake, which is out here, 20 kilometers away. Lake Tahoe is 1.5 times bigger than Utah Lake. But at 20 kilometers away, look at the nitrogen data. Both the nitrate and ammonium increased over a 20 kilometer distance and even higher over about a 50 kilometer difference. So how do you equate an ammonium paper to say ammonium is going to decrease and attenuate to 2,000 meters? Nope, it went up when you went to 20,000 meters. Okay, here's the SRP data. Okay, so this also is the same locations. So Mid Lake, it was about 18 or 20% lower than the Ward Lake site after 20 kilometers. Also, the variability in the data, and they went through statistically, it was not significantly different, okay, from the Ward Lake shoreline data. So there's a demonstration, evidence that this stuff travels a lot farther than 100 meters, both from the Van Kuren paper and from this JASB paper. Yet the document says, JASB et al., this is the support document, JASB et al. Sampled wet and dry deposition nitrogen and phosphorus in and around Lake Tahoe and found that deposition decreases significantly moving toward the middle of the lake. That's just not a true statement, looking at the data. What they did conclude was, as the differences between the stations had distributions that were asymmetric, i.e. skewed to the high values, okay, they used the sign test, but all differences for nitrate and ammonia were significant, while only the difference between the Ward Lake level and the South Lake Tahoe were significant. Okay, the other site at 20 kilometers out was not significantly different from the shoreline site. Okay, here's also out of the support document, here's the data after the outliers were removed. And this is the 2020 data, including the purple Bird Island data. Okay, so it looks to me, even though Michael said that it was 3 times, I don't think it looks like it's even close to 3 times higher once you took out the quote unquote designated outliers. Okay, this is right in the mix. Some data was high along with other sites. Some data were lower along with other sites. What does David Gay say? Bird Island data was in line with other episodic data, both high and low. Okay, so let's look at episodic data. Over again, I went and looked at the wind data at even the Provo Airport. There was 4 days in the week of sampling that before the week of sampling this data point, where all the other 4 sites had a spike. Okay. Let me go. All right, I'll get back to that one. Here's one of those 4 days. There's a wind speed clocked at 40 miles an hour. Okay, during the day before. There were 3 other days with 25 to 40 mile an hour winds during the week prior to that sample. Okay. So let's compare that with what was used when the group did a comparison of weather events. Did they use episodic high wind events? No. Average wind speed, daily wind speeds during the entire year of 2020 to January 2021. The mean speed in meters per second listed here, maybe about 3. If you multiply this by about 1.9, that's about the miles per hour. Okay, so this certainly reflects the average daily wind speed. Does that even look like an event like, like this event here? No, there are episodic windstorms that we all know about. We all know about these dust storms. There's another line of evidence from just this year. Steve Nelson used an active volumetric sampler. He had Bird Island, Mosida, and Provo High School. Okay, the same idea. So here's the Bird Island data. Collected just, he put a sample out there just for a couple of weeks. In the first the first sample collection, Bird Island was slightly higher than the shoreline sites. The second collection period, it was midline. The third, okay, it was actually below the other two sites, midline. Okay, below midline. So another line of evidence that it doesn't attenuate at Bird Island. And yes, these are small particles, probably in that 10 to 20 micron size.
All right. Thanks so much, Theron.
I didn't see the thing. Let me say one more thing about this.
Your time is up. You got to stop now.
I need to show this because he talked about Bird Island data. So in response to his accusation that Bird Island was contaminated, I visited that and there were no bird droppings. I went out there at least 15 times to carefully look for signs of contamination. There was none. I still took triplicate samples from a beach, from California Gulls. If droppings had hit the Bird Island bucket, one dropping would have raised the number to 1.11 milligram per liter. The average in the Bird Island bucket was only 0.27. So if it got hit by droppings, it would have been 4 times higher.
Okay, Theron, I'm going to ask you to stop now and adhere to the commitment that we all made for 20 minutes. I bet people will have questions that will give you a chance to talk more about that.
I'll be ready.
I bet. So if you'll unshare your screen so that you and or Mike and or Samuel and or maybe Kateri, I don't know, can pop up slides in response to questions. First of all, I would like to take a minute to thank Samuel and Mike and Theron, because as I said, 20 minutes feels like a long time until you're trying to say a bunch of smart stuff in 20 minutes. So thanks to everybody for all of that hard work. Now, steering committee in particular would love to hear your questions. As you can tell, the science panel, in particular the subgroup working on atmospheric deposition, had a very in-depth and quite lengthy conversation to ensure that they could bring you the best information possible. Would love to hear the questions that you might have for them. And Craig, I know that you are you're on the phone now, so if you have a question, you would raise your hand with *9. Who has a question for our lovely panelists? And there's Zach. Hi, Zach. Steering committee. I ushered him along so you could have time for questions. It'd be super great if you had some. Really? Really? Ha, Jesse's going to have a question for me. All right. Okay. We'll go to Sarah first. Sarah, go ahead.
Yeah. I'm curious regarding the question of insects in the samples. Dr. Brett made a comment that, while terrestrial input through insects into lakes happens naturally, that this wasn't the right way to study those relative inputs. And then you'd have to also look at the outflows through terrestrial or aquatic insects leaving the lake. So I'm just curious if that's been looked at or in other systems, like what percentage, I don't know. It seems to me that that's an important question, whether or not the atmospheric deposition sampling is how that should be taken into account or not.
Science panelist who wants to take a run at that? Mike, do you want to try that one? Hold on. Mike, go ahead, and then I'll give.
Okay, yeah. I think the majority opinion was that would require a separate study, and that would be nice if that was done, because there's a tremendous potential that there's a lot of biomass of chironomids leaving the lake, and for sure there's some biomass of terrestrial insects coming in, but there should be a dedicated study that has that as its objective. Probably would need sampling from more than 4 locations or 5 locations. It would need quite a bit more sampling than what's been done for AD. So I think it would be a good study, but it hasn't been done. And I'm not aware of other studies that have done it in real detail for other sites to try to quantify that, how much comes in and out. There might be, probably most of the studies that have done that kind of thing are probably actually being done on like fairly small streams, but not on larger systems like lakes. Like in a small stream, it would probably be pretty easy to show that terrestrial insects sometimes are an important flux into the stream. But I'm actually, Hans will be aware of this study as well, but I managed a research station at Castle Lake in Northern California for 6 years. And there was a paper published about a fall of migrating ants on the lake, flying ants that landed on the lake one time. And it was like this event that lasted for like 3 days. And during 3 days, there was a big input of terrestrial insects into the lake. But I managed that station for 6 years, and I never saw anything like that after that. I saw a lot of pollen falling into the lake, but I didn't see, any swarms of terrestrial ants, migrating ants falling into the lake.
You have a lot of really gross stories, Mike. Thanks. Farron, did you want to add anything to that?
Yeah, so, I read a paper, and I can't remember the citation, so it may not be accurate but as I recall, the other insects in the lake, of course, are vast majority midges. And we know that when they emerge, they go into these mating swarms, and they really don't try to fly away from the shoreline, because the females need to lay their eggs back in the lake or they're going to die. They got to be relayed back in the water. So I believe the number was probably an average within about 200 meters of the shoreline was the farthest known. And since the shoreline of Utah Lake is so gradual, it still would likely have fallen into, for example, the lake with surface or shoreline that would be inundated during the next spring runoff. So it'd be like returned or recycled within the lake. And that's how I interpret that. So I thought, well, it may not be as big an issue as the terrestrial contribution. That's how I treated it.
Thanks, Theron. Kateri, did you want to add something to that before we go to our next question?
Sure. I think the other thing to add is that there were some discussions on the science panel of whether the samplers were actually attracting insects rather than just capturing sort of transient background insects. So that was the other piece of, it would be interesting to see the fluxes of insects in and out of the lake, and then also our atmospheric deposition samplers the way to do that. And there was some concern that they would be overinflating the insect deposition.
So many factors. Thanks so much. Jesse, go ahead.
Yeah, thanks. I guess I think the way there with this is the majority against the Lone Ranger, or whatever you're calling yourself at that point. So I guess I got 2 questions: is how much do the minority and majority opinions change the final outcome? And what are we supposed to do with it? Are we supposed to vote at the end of this? Do we go with majority, minority? What are our next steps? So I just want to know, as a steering committee and as a science title, where do we go next? Do we just agree to disagree and move forward, or what are we doing? Because otherwise, I feel like I'm having deja vu for the last meeting.
Great, thanks. Who wants to tackle that one? Scott, do you want to answer that one, or John?
Yeah, I can hop in. Sorry, Jesse, your audio was a little garbled again. And I caught how much difference is the minority and majority opinion. And then what is the action to be taken? Is there a vote to come on this? And as I see it, it's, the recommendation was made through this process, pretty well vetted process. And then the majority recommendation would be passed along to the modeling team to incorporate. And we are in discussions of, there have been some commitments to incorporate the minority opinion into assessing model uncertainty. And so in the end, all of the recommendations will be passed on and assessed during the modeling, the water quality modeling portion of this project.
Thanks, Scott. Rich? You should be able to unmute now.
Thank you. My question is for Dr. Brett on your histogram chart that you had where you were showing the different percentiles. I don't know if you can pull that up again and kind of draw out where we would have like a 2 sigma or a 3 sigma capture of all the data. Hopefully that question is appropriate or understandable.
Mike?
I'm muted.
No, you're not.
Oh, okay, thank you.
Not amazing.
Yeah, you were all over it. Okay, so here's the figure I think that you're talking about. Can you see it? Can you see the figure?
He's nodding.
Okay,
I can't talk. They mute me and unmute me, but I was trying.
Okay, okay, thank you.
The
So,
system does it, but I think if you don't turn off your camera and don't do anything, Rich, and I don't do anything, you should be able to stay unmuted for this. Go,
okay.
Mike.
So you're asking questions about standard deviations?
Basically, yeah. I now realize this is not a normal distributed.
Yeah, it's not a normal distribution.
I
but
understand that.
I reported the results in terms of percentiles within the distribution. So, you know, what this plot shows, and if we actually go back to this plot, if you look at this, there's only been 6 observations of sediment accumulation in Utah Lake. It's only been reported 6 times. And so one of them was high and 5 were low. The one high estimate does match up with, you know, the higher estimates provided from the Williams memo. But the 5 lower estimates match up almost perfectly with the consensus estimate from the AD report. So, I mean, I guess one way you could look at that is not so much in terms of sigma, but in terms of, well, there's about a 5 out of 6 chance that the consensus estimate matches up really well with what we observe. And there's about a 1 in 6 estimate that the Williams data match up better with what we observe. You know, if the actual sediment accumulation rate in Utah Lake is actually as high as that 1 of 6 estimates, then the Williams estimates would be more plausible. But if the actual sediment accumulation in a lake is only about 2 millimeters per year, then the Williams estimates would not be very plausible.
Quick follow-up, Rich?
Yeah, I'm trying to basically come in with what Jesse's asking. When we're all done, what is our recommendation, or how are we from the steering committee going to give direction from this report to the model and go from there? So what I understand from what Dr. Brett said, and maybe you can clarify that, if I'm looking at the AD scenarios that are right next to those that you're pointing in, there's the 32 for the air deposition for the TerraTech consensus-based number. There's all these other numbers that are associated on there. There's 150 and 250. So there's a chance that the 250 could be an actual scenario from what you've told me.
The 250 is the 83rd percentile, and that actually matches up with the much higher sediment accumulation rate in this plot. So it matches up with 5 millimeters of sediment accumulating per year.
Okay. All right.
It doesn't match up at all with these other 5.
I got it. Yeah. Thank you.
Let's give Theron a chance to jump in on that one, and then we'll hear Gary's question. Theron, go ahead.
Yeah, as I mentioned several times in our meetings, the USGS did sedimentation sampling in Great Salt Lake, just a mere, 60, 70 miles away. And their numbers ranged from 4.5 to 5.5 millimeters per year in that data set. I haven't got that in front of me, but I recall those numbers. It was variable around the lake, but that was about, the range was between 4.5 and I believe up to 5.5 millimeters per year for Great Salt Lake sedimentation. So it could well fall in line with the Utah Lake data.
Thanks, Theron. Gary, go ahead and come off mute.
Okay, I'm kind of trying to follow up with what I thought Jesse was trying to say. I couldn't hear him very well. But is there some compromise between the two different opinions where we could do a test that we both agree? It'd be good to go forward where we had both entities agreeing. I know I'm an engineer, not a scientist, so I don't know how hard that is. But is there something that we could agree on as far as moving together to bring the two parties closer together? It's just a question. I don't know what that would be, but I think that might have been, so as we go forward, we got a better united front. I'm just asking the question, and I have no idea if it makes sense. So
your brain works like my brain, Gary, because as a facilitator, I'm like, surely there's a middle ground. And Scott, do you just want to say a quick minute before I go to our panelists, or John, either one of you, just to talk a little bit about sort of the modeling components and how that factors in here? I'm happy to unmute whichever one of you is going to jump in.
I guess I can try. Oh, go ahead, John.
Now it's everybody. Okay, John.
So Scott, why don't you go ahead and talk about the effort that goes forward and what's needed in terms of atmospheric deposition information to feed the model, and then if I need to comment further, I will.
Scott?
Okay, yeah, so as I said a moment ago, this information will be passed into the modeling team to inform the AD portion of the loading estimate. We need that to make the models run the right way. And what has unfolded in recent discussions with DEQ's executive director and John as a division director and the Wasatch Front Water Quality Council is an agreement to run the models with a wider range of estimates than what were originally planned. The plan was always to run a range of estimates to kind of address that idea of uncertainty, I think that Rich and Mike were just talking about. And now that range will incorporate the Wasatch Front Water Quality Council recommendation for atmospheric deposition. And so I think that addresses, I guess, the comment that Gary just had and Jesse, but yeah. So anyway, kind of a change of course to try to accommodate that range of perspective.
Well, and so if I may, if I'm still unmuted, I mean, I think that the deposition figure that Mike just showed is a pretty good thing to have in mind when we're looking at, you know, the variability, right? I mean, we've spent all this work, lots of time, lots of number crunching to get to this point, and the science is difficult. And so there's a distribution of answers. And, you know, we know that we have multiple runs that need to be done with the model just to evaluate scenarios, but we also know we need to look at its sensitivity. And, you know, within the range of studies and estimates that we've come up, it only makes sense that we are curious enough to investigate the broader range, both for sensitivity as well as, you know, does it matter or does it blow things up? Who wouldn't be curious enough to ask those questions? And so we will do that as part of sensitivity testing. We'll make sure to cast that wider net to the higher loading rates.
Thanks, John. I appreciate it. We'll hear from Mike, then from Rich, then from Theron, and then you'll see observers. I just popped into the chat that if you want to jump in during our public comment opportunity, now would be a good time to start raising your hands just so I have a sense of how much time to allow for that. All right, Mike, you should be ready to go.
Okay, thanks. So I wanted to make one point, and I put a lot of effort into finishing on time, so I left a slide out. I just want to throw this out there. We went through a very deliberate process and showed how we how we vetted these data, and we documented everything very carefully. I have read the Williams memo multiple times, and there's two numbers that come out of the Williams memo, 150 and 250. I've also extensively analyzed the raw data that it's supposedly based on, and I cannot figure out how these estimates were derived from those raw data. And I think that the minority estimate needs to be documented. They do not explain where 150 and 250 comes from. And so we have, you know, a very deliberate process where we came up with estimates. We made assumptions about, you know, how particles attenuate based on their size. You know, which samples might be contaminated with material that's not actually representative of the AD that we're interested in. And we laid it all out, and you can agree or disagree with any of what we said, but the alternative estimates don't have any detailed documentation showing where those numbers came from. They're just, there's, you know, an explanation of AD, and then there's like, you know, the conclusion is 150 and 250 without documentation. And I think that needs to be resolved.
Okay, thanks, Mike. All right, we're getting up to our public comment window. We do have two of our observers who are going to want to jump in, and I want to make sure that we reserve time for that, as is our commitment. So let's hear from Rich briefly, and then from Theron briefly, and then I'll go to those folks. Rich, you should be able to unmute now.
Thank you. I just recall as a steering committee, we met in one of our discussions, we went into great detail, even after conversation. We did a lot of emails going back and forth where we discussed the model and what we were going to put in the model. I think it's appropriate that we revisit that discussion again. It talks about that we would have a range of different values to put in this model. And I think it's appropriate that we cover ranges that cover what Dr. Brett had shown, that those values could be there. And in short, I'm saying range from, say, 45 to 450 would cover that range, and then something in the middle. And I think that's a completely appropriate from our previous discussions and with this information today.
Thanks, Rich. I'm not sure I can speak to that on a process level at this time, but let's hear from Theron. You should be able to unmute now.
Very
There you
good.
go.
Okay, yeah. Just to clarify, I got forwarded the memo from Kim Shelley, and the number that she agreed to is the 130 tons, which is the low end of what the Williams data range shows. Just to answer that, and Mike, there's a paper, I believe there was two papers came out similarly. One was by Tefler et al. And one was by Brown et al. One of those papers discusses how Williams got to those data points. So if that failed to get into the literature folder of the science panel, that might have been my fault, and I'm sorry. But if it's not there, I can certainly forward that paper to you. It's a publication as well. So that
I've read those papers multiple times, and it does not explain where 150 came from.
Okay, fellas. Theron, if you'll send that around just to make sure everyone has it, I'd sure appreciate getting that going. Thank you so much. John, do you want to say anything just about Rich's comment related to a go back to the steering committee regarding what the model might want to look like? John, where's John in my list? John, Maggie, there you go. Now you should be able to unmute, John. There you are.
Yeah, so there are ranges, right? The science panel came up with ranges, and you know, those should be the focus. In looking at broader ranges, you know, I looked at the data along with Scott and what had been, you know, floating around as appropriate alternative numbers in selecting the higher numbers. I don't think it makes sense. You know, the science panel has really narrowed it down to an appropriate range. I'm willing to step outside of it because, like I said, we should be curious enough to see how the model performs under those conditions. But I really think it needs to come from the science team. I want to be careful about just sort of arbitrarily selecting numbers.
Thanks, Mike. All right, we have time for questions from two of our observers. Observers, I will unmute you and allow you to talk if you'll ask a brief question, and then let us know if you have a specific person you'd like to hear from, or if, you know, if it's dealer's choice, I guess I could pick, but what the hell do I know? Steve Nelson, why don't you go ahead?
Okay, I've written my comments and questions out in bullet form, and so I'll just read them.
Okay.
I would like to know where the diatom counts can be found. In the main part of the lake, total phosphorus and nitrogen have not changed from pre to post settlement times, whereas planktic to benthic ratios have increased. So I would really like to be able to see those diatom counts and apply the transfer functions that we have used to them. I think right now we're leaving information on the table. I don't know if Janice is still on the call, but I've reached out. I would really like to look at those counts and see if we can reach some sort of consensus or understanding on what the diatoms say. When calcite grows over sorbed phosphorus, the phosphorus cannot desorb. We need to be sure that phosphorus that is structurally bound within the mineral, which is probably the majority of the phosphorus, cannot desorb. And then one final comment is that sedimentation rates do vary depending upon where you are in the lake system. The deposition rates are going to be high where you have stream inputs, therefore more detritus. I would expect the deposition rates near the eastern shore of the lake to be higher because that's where the wind blows and you will have a lot of lateral sediment deposition. So in my mind, there is no reason to minimize a 5 millimeter per year sedimentation rate. And if there are high deposition rates near the shoreline, downwind, we need to remember that those areas cover a lot of ground. That's a lot of sediment and a lot of underneath a lot of lake surface area.
Thanks, Steve. Janice, do you want to just respond to the specific question regarding the diatoms?
Yeah, I'm happy to share the data. Steve, sorry, you emailed in the thick of a semester of teaching 3 classes and it slipped my mind. And I also put the data up on a repository, so it's publicly available, but I will send you the file.
Thanks, Janice. Really appreciate that. And David Richards, did you have a question or comment for the bunch?
I do. Can you hear me?
Sure can.
Okay. My apologies. I missed the public comment period that we had at 2:10. I stepped out of the room, so maybe someone could update me on what the public had to say at 2:10. And then I wanted to talk a bit about outliers and contamination. They don't make any sense to me why we're not using those. First off, I did analysis on the Barris data, and I found that Bird Island was significantly higher than the Orem and Mosita sites, but not significantly higher than Lakeshore or Pump Station. So Bird Island falls right in the middle of those. But as far as outliers are concerned, the science panel used the interquartile range for the high range to get rid of the outliers. I don't think that was appropriate because most of the atmospheric deposition comes from the high wind storm events. And as an analogy, I looked at Las Vegas and Provo rain events. Since Las Vegas, since 1895 to 2024, there was 44,000 days without precipitation, and there was 2,700 days with precipitation. So that would be 5.8%. had precipitation, and according to the science panel's logic, they would throw out the rain events in Las Vegas. Same with Provo. There was 34,000 days without rain since 1916 and 49,000 days with rain. So that was an outlier, about 12.4%. So in the science panel's logic, they would throw out those outliers too. So I don't know why we're throwing out outliers whatsoever. It makes no sense whatsoever from my statistical background. And as far as contamination from the insects, I think all the insects were removed before the nutrient analysis were conducted. And they were processed less than a week since the samples were left out. So I do not think the insects, so what the contamination is saying, what you guys are saying with contamination is that the insects leaked nutrients into the water because the insects were removed from the analysis. So insects are not going to leak nutrients into the water because they have impervious cuticle layers, but they do have some intersegmental membranes that are semi-pervious. But you have to realize they were in distilled water. So they're going to be taking in distilled water. And if you ever looked at some bugs floating in the water, they start to take on water, and they get fatter and fatter from taking water in. So they're actually going to be taking the water in and not out. So I do not see why you would think, due to osmotic pressure, I do not see why you would call those contaminations when they actually might have been reducing the nutrient concentrations in the water. That's what I had to say.
Thanks, David. And David, what I'll tell you is there were no hands up when I mentioned in the chat that it was, I was asking for public comment hands during that first break. Super speed round, folks. We're at the end of our time. Kateri, you wanted to say something real quick?
Sure, I can just provide an update. Just to be perfectly clear, there were no outliers that were removed simply because they were statistical outliers in the data. That was simply used as an exploratory approach to look at, when we were seeing high samples of atmospheric deposition, what might have been the cause. The only samples that were removed were those that had contamination, and then those estimates those atmospheric deposition rates were estimated based on a regression approach that incorporated things like the wind speed and particulate matter concentration. So anything that would have happened during that time was then imputed back. So we weren't necessarily throwing out observations, but rather replacing contaminated samples with an estimate that pertained more to the episodic nature of atmospheric deposition. But just to be perfectly clear, there were no outliers, statistical outliers, that were removed from the analysis whatsoever.
Thanks, Kateri. Mike, ever so briefly?
Yeah, I also wanted to comment about the insects not leaching nutrients out. I mentioned that there were 6 Saratoga samples that were identified as being contaminated with insects, and they had 1,000 times higher nutrient concentrations than the median for the uncontaminated samples. And the Olson paper specifically said that the Saratoga Springs samples collected in July and June and July were contaminated with sweat bees. And those were the samples that were 1,000 times higher than the
All right. Thank you, Mike. And last chance here, and then we're going to close this one out. Go ahead.
Okay, just a little rebuttal. Those samples followed, I didn't have time to show the wind records, but those followed high wind events, not just the introduction of a few bees into the sample. That was the issue.
Okay. All right. First thing, what would it be like if our presidential debates were as civil as this? Like, what a different world that would be, that people can disagree and be so lovely to one another. Thank you all very much for your thoughtful conversation today. In particular, want to make sure that you take a minute just to reflect on the tremendously difficult and lengthy work that has been done by the science panel as a whole and by our particular subgroup focused on atmospheric deposition. There was so much that they did agree on, not just on this topic, but also, as Kateri observed in her charge questions overview, related to some of the other issues. So please don't interpret what you've heard today as, oh my gosh, there's so much debate. There have been some really hard conversations, but there's a really fair discussion going on and a lot of agreement. And all of these science panel members are just so lovely and try so hard to find common ground. So thanks to all. Steering committee members, you should be hearing from Samuel in the near future. We have more things to discuss. I personally, as I think you all are tired of hearing, I'm so excited for phase 3, I can't even stand it. So I'm looking forward to that. Science panelists, you know you have more things to do, and we'll look forward to visiting more with you here in the weeks ahead. For everybody, thank you for taking so much time out of your day. We will follow up with you about next steps on some of those charge question conversations. If you didn't have a minute to put your preference for future conversations in the chat, you can follow up with Samuel by email. Today was not your last chance. And I mean, you could read the whole thing and then follow up. That'd be fun too. Be well, do good stuff, and we'll have more conversations with you in the weeks and months ahead. Happy New Year, everyone. Thank you so much for your attention today. We're adjourned.